There are mysteries above us that are older than Earth itself. Invisible forces shaping galaxies. Light that began its journey billions of years ago. Black holes that bend time. Entire regions of space we cannot see, only infer. These aren't science fiction, they are real, documented, measured, yet still profoundly mysterious. How did the universe begin? What is dark matter? Are we alone? And perhaps most comforting of all, how small are our worries beneath such vast skies? Before you settle in, get comfortable. Dim the lights. Maybe let a fan hum softly in the background. And if you enjoy these late-night cosmic wanderings, consider subscribing. Tell me where you're listening from and what time it is there. I always love seeing how far across the planet these quiet journeys travel. Now, let's drift upward. Before there were stars, before there were galaxies, before space stretched quietly in every direction, there was something far stranger. Not darkness, not emptiness, not even silence. Those require space to exist within and time to move through. In the very beginning, neither space nor time existed in the way we understand them now. Tonight we begin at that edge, not at a place, but at the birth of places. Not at a moment, but at the birth of moments themselves. If you could rewind the universe like a slow-moving film, watching galaxies drift closer and stars collapse back into clouds, you would see everything compressing inward, denser, hotter, brighter. Clusters of galaxies would merge into a single luminous field. Distances between stars would shrink. Atoms would lose their structure. Electrons would no longer orbit. Protons and neutrons would dissolve into energy. Continue rewinding, and all the light in the universe would compress into something blinding and impossibly small. Every star that has ever burned, every planet that has ever formed, every atom in your body, contained within a state smaller than an atom itself, smaller than the smallest scale our current physics can fully describe. This is what we call the Big Bang. But the name can be misleading. It was not an explosion in space. It was the expansion of space itself. There was no center. There was no edge. There was no empty void waiting to be filled. Space was not a stage upon which the event occurred. Space was part of the event. It was being born. Imagine dots drawn on the surface of a balloon. As the balloon inflates, each dot moves away from every other dot. None of them sit at the center of expansion, because the center is not on the surface at all. In the same way, when the universe began expanding, every region moved away from every other region. Galaxies today are not flying outward from a specific point in space. They are being carried apart because the fabric between them is stretching. Nearly 13.8 billion years ago, the universe existed in a dense, hot state where energy and matter were indistinguishable. Temperatures were beyond comprehension. The forces we now think of as separate, gravity, electromagnetism, the strong and weak nuclear forces, may have been unified into a single interaction. The universe was not chaotic in that instant. It was simple, smooth, and almost perfectly uniform. Then it began to expand. As space expanded, it cooled. Cooling allowed energy to settle into particles. Particles combined into protons and neutrons. Within minutes, those formed the simplest atomic nuclei, mostly hydrogen and helium. For hundreds of thousands of years, the universe remained a glowing fog. Light could not travel freely. Photons scattered constantly through a dense plasma of charged particles. Then, around 380,000 years after expansion began, the universe cooled enough for electrons to join with nuclei. Neutral atoms formed, and suddenly light was free to travel. That light still moves through the cosmos today. It fills all of space as a faint microwave glow, stretched and cooled by billions of years of expansion. It is ancient light, a quiet afterglow from a time when the universe was young. When we look far into space, we are looking back in time. But this faint radiation lets us look further than any galaxy, to a time when structure had barely begun. Within that glow are tiny fluctuations in temperature, almost imperceptible variations that would eventually grow into galaxies, clusters, stars, and planets. From those subtle ripples came everything complex. Yet as comforting as this unfolding story may feel, It leads to a question that naturally arises. What happened before? If the universe began expanding 13.8 billion years ago, what came earlier? The question seems simple, but it assumes something profound. That before is meaningful. Time as we experience it flows steadily forward. Seconds follow seconds. Causes precede effects. But in modern cosmology, time itself began with the expansion. It is not something separate from the universe. It is woven into its structure. To ask what happened before the Big Bang may be like asking what lies north of the North Pole. The question feels reasonable, yet it depends on a direction that ceases to exist beyond a boundary. If time began with the expansion, then before may not be a physical concept. Not because we lack imagination, but because earlier may simply not exist in a meaningful way. Still, physicists are not entirely satisfied with leaving it there. Some theories suggest the Big Bang was not an absolute beginning, but a transition, perhaps a bounce from a previous contraction, or a fluctuation within a larger cosmic landscape. Some models imagine space emerging from deeper quantum relationships. Others suggest time itself may not be fundamental but arises from changes in entropy. These ideas are elegant and intriguing, yet the honest answer remains quiet and simple. We do not know. Our equations carry us back to fractions of a second after expansion began. Observations of cosmic background radiation, galaxy distributions, and expansion rates give us confidence in the early picture. But when we approach the very first instant, our theories falter. General relativity predicts a singularity, infinite density and temperature. Quantum mechanics resists such infinities. The two frameworks, each remarkably successful in their domains, do not yet fully agree at that boundary. At the beginning, our best understanding reaches its limit. It is humbling to consider that everything we know emerged from that early state. The calcium in your bones was forged in stars formed from primordial hydrogen. The oxygen you breathe was born in stellar cores. The iron in your blood was created in exploding supernovae. All of it traces back to that dense, hot beginning where complexity had not yet unfolded. You are not separate from that event. You are a continuation of it. The universe expanded. It cooled. Structure formed. Stars ignited. Galaxies assembled. Chemistry grew more intricate. Awareness emerged. And now here you are, listening to the story of how it began. There is something calming in that continuity. The Big Bang is not merely a violent origin. It is the beginning of a slow unfolding, expansion stretching steadily across billions of years. Even now, space continues to stretch. Galaxies drift farther apart. The expansion has not stopped. In fact, it is accelerating. But that is a mystery for another moment. For now, imagine the universe once smaller than an atom, now vast beyond comprehension. A single hot beginning evolving into a cool, spacious cosmos filled with quiet stars. Beyond that beginning, we do not yet see clearly. Perhaps there was no before. Perhaps there was something timeless and unfamiliar. Perhaps our concept of beginnings is incomplete. It is enough tonight to rest at that edge, at the birth of space and time, where the universe was young, simple, and luminous. Let the scale of it stretch your thoughts gently outward. Let the mystery soften the need for certainty. The origin has been unfolding for nearly 14 billion years. It can remain unsolved while you rest. Imagine the early universe expanding, cooling, becoming transparent and calm, from a dense hot state to the vast night sky above you now. Somewhere along that long unfolding, a small planet formed. On that planet, a quiet room. In that room, a listener drifting towards sleep. The universe began without space, without time, without stars. From that beginning, without before, came everything. Let that thought settle softly. Let the expansion carry you outward, and we will continue gently into the ancient light that still surrounds us. Long before the first star ignited, before galaxies spiraled into graceful shapes, before planets circled quiet suns, the universe glowed, not with starlight, not with the focused brilliance of fusion, but with a diffuse radiance that filled every direction at once. In its earliest era, the cosmos was not dark at all. It was luminous everywhere, a hot and uniform sea of light and particles so tightly bound together that illumination had no freedom to travel. If you could have existed in that distant epoch, you would not have seen through space. You would have been immersed in brightness itself, surrounded on all sides by an unbroken fog of energy. In those first hundreds of thousands of years after expansion began, the universe remained dense and intensely hot. Protons and electrons moved freely, unable to join into stable atoms because the temperature was simply too high. Photons, particles of light, bounced constantly off these charged particles, scattering again and again in every direction. Light couldn't stream across the cosmos. It ricocheted endlessly like a beam trapped inside a cloud. The universe, though radiant, was opaque. There were no clear skies, no distant horizons, no long paths of travel. Everything existed within a glowing plasma where matter and light were inseparable dance partners. As expansion continued, space stretched and temperatures gradually fell. Cooling didn't happen abruptly but steadily, like embers dimming as they spread apart. Eventually, roughly 380,000 years after the beginning, conditions changed in a subtle yet transformative way. The universe cooled enough for electrons to slow down and bind with protons, forming neutral hydrogen atoms. This process is known as recombination, though in truth it was the first time such stable unions occurred. When electrons settled into place around nuclei, the charged fog dissolved. Photons were no longer scattered incessantly. For the first time, light could travel freely across the expanding cosmos. That moment was not dramatic in the way explosions are dramatic. There was no flash, no sudden roar. Instead, it was a quiet release. Light that had been trapped was suddenly free to move unimpeded. Streaming outward in every direction, the universe became transparent, and that ancient light, set loose nearly 14 billion years ago, has been traveling ever since. It has crossed unimaginable distances, stretching along with space itself, cooling as wavelengths lengthened, yet never ceasing its journey. Today, that first light still fills the universe. It surrounds us from every direction, not visible to human eyes because expansion has shifted it into the microwave portion of the spectrum. This faint glow is called the cosmic microwave background. It is not concentrated in stars or clustered in galaxies. It is everywhere, a uniform bath of radiation permeating all of space. If you could tune your senses to microwave frequencies, the sky would not appear dark at all. It would shimmer softly with this ancient afterglow, a relic from the time when the cosmos first became transparent. The discovery of this radiation was not planned as a triumphant confirmation of cosmological theory. In 1964, two radio astronomers, Arno Penzias and Robert Wilson, were calibrating a sensitive microwave antenna when they encountered a persistent hiss that would not disappear. They checked for equipment faults, cleared out nesting pigeons from the apparatus, and accounted for every conceivable terrestrial source of interference. Yet the faint signal remained, coming equally from all directions in the sky. It was uniform and steady, impossible to attribute to local noise. What they had detected was the whisper of the early universe itself. The accidental discovery confirmed a bold prediction. If the universe began in a hot, dense state, there should still be residual radiation lingering from that era. When scientists measured the temperature of this background glow, they found it astonishingly uniform, about 2.7 degrees above absolute zero. That temperature is unimaginably cold compared to stars. Yet it represents a cooled remnant of something once blisteringly hot. Over billions of years, as space expanded, the wavelengths of those ancient photons stretched, reducing their energy. What was once brilliant light is now a faint microwave hum. The expansion of the universe has effectively redshifted this primordial radiation into gentleness. Yet the cosmic microwave background is not perfectly uniform. Embedded within it are tiny fluctuations, minute variations in temperature on the order of 1 part in 100,000. These variations are so small that without precise instruments they would be imperceptible. But they are crucial. They represent slight differences in density in the early universe, regions where matter was just a bit more concentrated than average, and regions where it was slightly less so. These subtle ripples were the seeds from which all later structure would grow. Imagine a calm pond at dawn, its surface almost perfectly smooth, disturbed only by faint ripples. Those ripples, though delicate, determine how patterns form as the water moves. In a similar way, the early universe was astonishingly smooth, but not entirely featureless. Gravity acted patiently on those denser regions, drawing matter inward over millions and billions of years. The slightly heavier pockets attracted more material, growing gradually into vast clouds. Within those clouds, the first stars ignited. Around clusters of stars, galaxies assembled. The cosmic web, an intricate network of filaments and voids, emerged from those initial irregularities imprinted in the microwave background. The cosmic microwave background, then, is more than ancient light. It is a map of potential. It shows us the blueprint from which galaxies were built. When satellites like COBE, WMAP, and Planck measured this radiation in exquisite detail, they revealed a delicate mottling of warmer and cooler spots across the sky. Each tiny variation corresponds to a region in the early universe that would one day influence the arrangement of cosmic structures. By studying these patterns, scientists can infer the composition of the universe, how much ordinary matter it contains, how much dark matter contributes to gravitational pull, and how dark energy shapes expansion. It is remarkable that from a faint microwave glow we can extract such profound information. The background radiation carries encoded within it the parameters of cosmic history. It tells us the universe is spatially flat to extraordinary precision. It confirms that ordinary atoms make up only a small fraction of total matter. It reveals that dark matter outweighs visible matter several times over. And it supports the idea that expansion has been ongoing for billions of years. All of this knowledge arises from light that began its journey before stars even existed. When we look at the cosmic microwave background, we are not simply observing old light. We are observing the universe in its infancy. It is a baby picture of everything. Just as a photograph of a child contains hints of who that person will become, this image of the early cosmos contains the outlines of all future structure. The fluctuations were tiny, but they held immense consequence. Without them, gravity would have had no variations to amplify. Matter would have remained evenly distributed, and galaxies might never have formed. The universe would have been a thin, diffuse haze without complexity. Consider how delicate that balance was. If the early universe had been perfectly uniform, structure would not emerge. If it had been too uneven, gravity might have caused rapid collapse into black holes before stars could ignite. Instead, the fluctuations were just right, small enough to preserve overall smoothness, yet large enough to allow gradual growth. The cosmos walked a narrow path between chaos and stagnation. That faint mottling in the microwave sky is evidence of this fine balance. As space continues to expand, the cosmic microwave background becomes ever more stretched and faint. In trillions of years, observers in distant galaxies may no longer detect it at all. The wavelengths will grow so long and the energy so diluted that it will fade beyond measurable limits. But for now, we live in an era when the afterglow is still visible to our instruments. We are able to see, in a literal sense, the earliest light that ever traveled freely. There is something quietly poetic in that. The universe has not erased its beginnings entirely. It has preserved them in a subtle radiance that permeates all of space. Imagine standing beneath the night sky, aware that beyond the visible stars there exists a deeper glow, an invisible ocean of ancient photons washing over you from every direction. Every second, countless microwave photons pass through your body, remnants of the early universe that have traveled uninterrupted for nearly 14 billion years. They are indifferent to your presence, yet they connect you to the earliest epoch of cosmic history. You are bathed in the same light that once illuminated the newborn cosmos. The cosmic microwave background also reinforces the idea that the universe has no preferred center. The radiation appears nearly identical in every direction we look. This isotropy suggests that, on the largest scales, the cosmos is uniform and homogeneous. Wherever an observer might stand, in this galaxy or another billions of light years away, they would see a similar glow. There is no special vantage point. The early universe was not centered on us nor on any particular region. It was expansive and impartial from the start. As you let your thoughts drift across these vast timescales, notice how gently the story unfolds. There was no sudden leap from chaos to complexity. There was cooling, gradual transparency, slow gravitational gathering. The first light did not blaze in isolation. It quietly filled space, carrying within it the faint signatures of everything to come. Those tiny fluctuations, amplified over billions of years, led to spiral galaxies and elliptical clusters, to stellar nurseries and planetary systems, to oceans and atmospheres, to consciousness itself. All of it traces back to subtle variations imprinted in that early glow. And so, when we speak of the cosmic microwave background, we are speaking of origin without drama, of evidence without spectacle. It is a quiet field of radiation that surrounds us always, a reminder that the universe once shimmered uniformly before stars punctured the darkness. It is the echo of a time when space had just become transparent and light began its long journey outward. That journey continues still, crossing the widening cosmos, whispering to us about infancy, about simplicity, about the first moment the universe became visible to itself. As you settle deeper into this thought, imagine that ancient light stretching across billions of years, thinning and cooling, yet never ceasing. Imagine it passing silently through galaxies forming, stars igniting, planets assembling, civilizations rising and fading. Through all of it, the background glow persists. It is patient, indifferent, steady, a baby picture of everything, still hanging quietly in the vast hallway of space. And in that faint microwave hum, the early universe continues to echo, soft, uniform, and filled with the seeds of all that would ever be. After the universe released its first light and became transparent, it entered a long and patient era, often called the cosmic dark ages. The glow of the microwave background still filled space, but no stars yet burned. There were no galaxies shining in clusters, no constellations tracing patterns across the sky. The cosmos was vast, expanding and quiet. Hydrogen and helium, formed in the earliest minutes, drifted through space in enormous diffuse clouds. Gravity, subtle but persistent, began its slow work. It gathered slightly denser regions together, drawing matter inward over millions of years. There was no urgency to this process. The universe had time. Within those faint density variations left behind in the early radiation, gravity began to amplify differences. Regions just a little denser than average pulled in surrounding gas. The gas compressed gradually, warming as it contracted. Over immense stretches of time, those clouds became thicker and more concentrated. Eventually, in certain pockets of the expanding cosmos, gravity overcame the outward pressure of gas. Collapse accelerated. Temperatures rose. And at last, something extraordinary happened. Nuclear fusion ignited. The first stars were born. But these were not stars like our sun. They were not modest, middle-aged spheres of hydrogen burning quietly for billions of years. The earliest stars, often referred to as population 3 stars, were giants, formed from pristine hydrogen and helium, untouched by heavier elements. They behaved differently from stars born later in cosmic history. Without metals, astronomers use that word to describe all elements heavier than helium, the cooling processes inside their natal clouds were less efficient. As a result, gravity gathered much larger amounts of material before ignition occurred. The first stars were enormous, some estimated to be tens or even hundreds of times more massive than the Sun. Imagine a star so massive that it dwarfs anything visible in today's sky. These primordial giants burned with extraordinary intensity. Their cores reached staggering temperatures, far exceeding those of typical modern stars. Fusion reactions proceeded rapidly, converting hydrogen into helium at an astonishing pace. Because they were so massive, their lifespans were brief, perhaps only a few million years. In cosmic terms, that is the blink of an eye. The first stars lived fast and died young, yet during their short lives they accomplished something transformative. They forged the first heavy elements. In the beginning, the universe contained only the lightest ingredients: hydrogen, helium, and trace amounts of lithium. The periodic table we know today did not yet exist. Carbon, oxygen, nitrogen, silicon, iron, all the elements that make rocky planets, oceans, and living organisms were absent. The cosmos was chemically simple, but inside the cores of these massive primordial stars, gravity created conditions intense enough to fuse helium into heavier nuclei. Through successive stages of fusion, new elements formed. Carbon emerged, oxygen followed. As temperatures climbed even higher in the most massive stars, fusion progressed toward silicon and eventually iron. This process was not gentle. It was a fierce balancing act between gravity pulling inward and radiation pushing outward. When fusion fuel began to run low, the equilibrium faltered. For the most massive of these early stars, collapse happened catastrophically. The core imploded under its own gravity, triggering a supernova explosion of staggering power. In those final moments, temperatures and pressures became so extreme that elements heavier than iron formed in rapid bursts of nuclear reactions. Gold, uranium, and other heavy elements were synthesized in the violence of stellar death. These explosions were not quiet endings. They were luminous events that outshone entire galaxies for brief periods. The supernovae of population 3 stars scattered newly forged elements into surrounding space, enriching the once pristine hydrogen and helium clouds. For the first time, the universe contained the building blocks necessary for rocky worlds and complex chemistry. The cosmos had changed permanently. None of those first stars survive today. Their enormous masses guaranteed short lifetimes. Even the smallest among them would have exhausted their fuel billions of years ago. What remains are only indirect traces, chemical fingerprints imprinted in later generations of stars. Astronomers search for extremely metal-poor stars in the Milky Way's halo, hoping to glimpse evidence of early enrichment. These ancient stars, though not primordial themselves, carry subtle signatures of the first stellar explosions. In their atmospheres, we find patterns of elements that hint at the nature of those long-vanished giants. Picture the early universe after the first supernovae. Space was no longer chemically simple. Clouds once composed solely of hydrogen and helium now contain traces of heavier elements. These new ingredients changed everything. Metals allow gas to cool more efficiently, radiating energy away and enabling clouds to fragment into smaller clumps. This meant that subsequent generations of stars formed differently. Instead of producing only enormous giants, enriched gas could create stars of varied masses, including smaller, longer-lived stars like our Sun. The deaths of the first stars made possible the diversity of stellar life that followed. In this way, the primordial giants were both pioneers and architects. They illuminated the dark ages and seeded the cosmos with complexity. Without them, there would be no carbon to form organic molecules, no oxygen to bind with hydrogen into water, no silicon to shape rocky planets. The very atoms that compose your body were forged in stars that lived and died long after those first luminous beacons. Yet the chain of creation begins there. The earliest stars initiated a cycle of birth and death that continues to this day. It is remarkable to consider how quickly the universe transitioned from simplicity to complexity. For hundreds of thousands of years, it was a smooth, glowing plasma. Then came darkness as expansion cooled it further. Then, within a few 100 million years, the first stars ignited, flooding the cosmos with ultraviolet radiation. Their light began to ionize surrounding hydrogen once again, gradually lifting the universe out of its neutral state in a process known as reionization. The cosmos did not remain dark for long. The first stars transformed it into a place of brilliance. The radiation from these giants traveled outward, carving bubbles of ionized gas into the intergalactic medium. As more stars formed, these bubbles expanded and merged. Eventually, most of the hydrogen in the universe became ionized once more. This era marked the end of the cosmic dark ages and the beginning of a universe filled with luminous structure. The earliest galaxies likely assembled around clusters of these massive stars, their gravitational influence drawing gas inward. to form larger systems. Yet despite their importance, we have never directly observed a population 3 star. Their light shone billions of years ago, and their lifespans were fleeting. Detecting them requires looking so far back in time that their faint signatures are nearly impossible to isolate. Modern telescopes aim to peer deeper into cosmic history, searching for galaxies that formed within a few 100 million years after expansion began. Within those galaxies may lie indirect evidence of primordial stars, but the stars themselves are gone. There is something poetic in that disappearance. The first stars existed only briefly, yet their influence persists everywhere. They were like sparks that lit a long-burning fire, vanishing quickly but leaving behind warmth and complexity. Every heavy element in existence traces its lineage to stellar furnaces. Even the iron in your blood and the calcium in your bones are products of nuclear reactions in stars that lived and died long ago. The cosmos is not static, it is generational. Each wave of stars inherits material enriched by its predecessors. Consider the contrast between those primordial giants and our Sun. The Sun is a third-generation star, composed of gas enriched by countless previous explosions. Its mass is modest, allowing it to burn steadily for billions of years. It shines with a calm persistence, nurturing life on at least one orbiting planet. But its existence depends on ancient ancestors that lived violently and briefly. The earliest stars created the conditions for stability later on. Their ferocity made possible the quiet longevity we now depend upon. If you imagine standing in the universe before any stars formed, the sky would have been utterly dark once the microwave glow faded beyond visible wavelengths. There would be no pinpoints of light, no galaxies glowing in clusters. Then, gradually, the first massive stars would ignite, isolated at first, then more numerous. They would blaze intensely against the darkness, burning brighter than most stars ever would again. Their ultraviolet radiation would carve shapes into surrounding gas. Their deaths would scatter glowing debris. The cosmos would awaken. Over time, galaxies assembled around these luminous centers. Gravity sculpted swirling disks and elliptical bulges. Stars formed in clusters, some massive and short-lived, others smaller and enduring. Planetary systems emerged in the enriched material. Chemical complexity increased. The periodic table expanded its influence into molecular clouds and rocky surfaces. The universe began to resemble something more intricate than a uniform sea of particles. Yet none of that complexity erases the fact that the first stars are gone. They left no surviving descendants in their original form. Their absence is total, their legacy indirect. We infer their existence from theory, from simulations, from patterns of elemental abundance in ancient stars. They are ghosts in the cosmic narrative, unseen but indispensable. As you let your thoughts drift across these early epochs, notice how much unfolded from simple beginnings. Hydrogen and helium, drawn together by gravity, ignited nuclear fusion. Fusion forged heavier elements. Explosions dispersed those elements into space. Enriched gas formed new stars and galaxies. From those processes came planets, oceans, atmospheres, and eventually life capable of reflection. The first stars did not know they were shaping a future. They burned because gravity demanded it and physics allowed it. Their brief brilliance set the stage for everything that followed. And now, billions of years later, you exist in a universe still illuminated by countless stars, each one part of a long lineage. When you look at the night sky, you are seeing the continuation of a story that began with those primordial giants. Though none survive, their influence remains woven into every luminous point. The cosmos you inhabit is richer because they lived. Let that thought settle gently. The earliest stars were enormous and short-lived, forging the first heavy elements in their intense cores. Their deaths seeded the universe with possibility. None remain today, yet without them there would be no later generations of stars, no planets, no chemistry complex enough for awareness. Their absence is complete, but their contribution is everywhere. In the quiet of the present universe, beneath the steady glow of familiar constellations, the legacy of the first stars continues, silent, foundational, and immeasurably profound. When we look up at the night sky, it feels open and endless. Stars scatter in every direction, and the darkness between them seems to stretch without boundary. But the feeling of vastness is not the same as understanding shape. The earth feels flat beneath our feet, yet we know it curves gently into a sphere. In the same way, the universe may feel infinite and unbounded, but its true geometry is a deeper question, one that scientists have been trying to answer for generations. Is space flat? Does it curve? Could it wrap around itself in ways that defy ordinary intuition? These questions are not poetic metaphors. They are precise physical inquiries about the structure of reality itself. To explore the shape of the universe, we must first understand what shape means on cosmic scales. Geometry at its core describes how space behaves. In flat geometry, the kind taught in school, parallel lines never meet, and the angles of a triangle always add up to 180 degrees. This is Euclidean space, familiar and comfortable. But on curved surfaces, these rules change. On the surface of a sphere, like Earth, parallel lines can converge. Lines of longitude, for example, begin apart at the equator and meet at the poles. Triangles drawn across large distances on a sphere have angles that add up to more than 180 degrees. Geometry bends to match the surface. Now imagine extending that idea beyond two-dimensional surfaces into three-dimensional space itself. The universe may not simply contain curved objects within it. Space itself could be curved. This concept arises naturally from Einstein's general theory of relativity, which describes gravity not as a force pulling objects together, but as the curvature of space-time caused by mass and energy. Massive objects bend space around them, shaping how light and matter move. If mass can curve space locally, perhaps the entire universe has a global curvature as well. There are three broad possibilities for cosmic geometry. The first is flatness, meaning that on the largest scales, space obeys Euclidean rules. In such a universe, parallel lines remain parallel, and the angles of enormous cosmic triangles add up to 180 degrees. The second possibility is positive curvature, similar to the surface of a sphere. In that case, space is finite yet unbounded, meaning you could travel in one direction and eventually return to your starting point without encountering an edge. The third possibility is negative curvature, resembling a saddle shape, where parallel lines diverge and triangles have angles summing to less than 180 degrees. Each scenario carries profound implications about the size, fate, and structure of the cosmos. How can we measure something so vast? We cannot step outside the universe to view it from afar. Instead, we rely on light that has traveled for billions of years, carrying with it subtle clues about geometry. The cosmic microwave background, the ancient radiation released when the universe became transparent, provides one of the most precise tools for this investigation. Within that faint glow are patterns of temperature fluctuations whose sizes depend on the curvature of space. By measuring how large these fluctuations appear to us, scientists can infer whether space bends or remains flat. The results have been astonishingly precise. Observations from satellites such as WMAP and Planck indicate that the universe is remarkably close to flat. The margins of error are tiny. On cosmic scales spanning billions of light years, space appears to follow Euclidean geometry. Parallel lines do not converge or diverge in any measurable way. Triangles drawn across immense distances add up almost exactly as they would on a flat sheet of paper. The universe, as far as we can tell, is geometrically flat, but flat does not necessarily mean infinite. This is where intuition begins to falter. A flat surface can extend forever, but it can also wrap around in more complex ways. Consider a video game screen where moving off one edge causes you to reappear on the opposite side. The surface feels infinite to the character moving within it, yet it is finite and loops back on itself. In mathematics, shapes like a torus, a donut form, can have flat geometry locally while possessing global structure that reconnects distant regions. In such a universe, you might travel far enough in one direction and eventually arrive where you began, without ever encountering a boundary. Could our universe loop back on itself? The possibility is not ruled out. If space were finite but unbounded, light traveling long enough distances might circle around and create repeating patterns in the sky. Astronomers have searched for such patterns in the cosmic microwave background, looking for matching circles of temperature fluctuations that would indicate light wrapping around a closed cosmos. So far, no definitive evidence has been found. The observable universe appears consistent, with flatness extending far beyond what we can see. Yet beyond the horizon of observation, geometry remains uncertain. The observable universe is limited by the speed of light and the age of cosmic expansion. We can only see as far as light has had time to travel since the beginning. That sphere of visibility spans about 93 billion light-years in diameter, accounting for expansion. Beyond that horizon, there may be more universe, perhaps infinitely more, or perhaps space curves gently on scales too vast for us to measure. Our instruments cannot peer beyond the boundaries set by light's finite travel time. The true global shape could extend far beyond our reach. Negative curvature presents another intriguing possibility. In a saddle-shaped universe, space expands in a way that diverges more rapidly than in flat geometry. Such a universe would likely be infinite, stretching outward without repetition. Triangles would have angles adding up to less than 180 degrees, and parallel lines would drift apart. While current measurements strongly favor flatness, the possibility of slight negative curvature remains within tiny margins of uncertainty. The cosmos could be so gently curved that its deviation from flatness is imperceptible across observable scales. Positive curvature, on the other hand, would imply a finite cosmos. Like the surface of a sphere, it would have no edges, yet its total volume would be limited. If you travel far enough in one direction, you might eventually return to your starting point. Such a universe could also influence its ultimate fate. In earlier cosmological models, positive curvature was associated with eventual recollapse, a scenario where expansion would halt and reverse into a big crunch. However, the discovery of accelerating expansion due to dark energy complicates that connection. Geometry and destiny are linked, but not in simple ways. When we speak of curvature, it is important to remember that we are describing three-dimensional space embedded within four-dimensional space-time. Visualizing this is inherently difficult. We rely on analogies, balloons, saddles, donuts, to hint at possibilities. Yet the true structure may not resemble any everyday object. Mathematics guides our understanding where imagination struggles. Equations describe how light travels, how distances scale, how geometry interacts with energy density. Through observation and theory, we approach clarity without ever stepping outside the cosmos to confirm it directly. The idea that space could loop back on itself is particularly fascinating. Imagine sending a beam of light into space, perfectly straight. If the universe were finite and positively curved, that beam might one day return from behind you. Having traversed the entire cosmos, you could, in principle, see the back of your own head, not as a mirror reflection, but as ancient light completing a cosmic journey. The timescales required for such travel would exceed billions of years, and cosmic expansion might stretch the path faster than light could complete it. But the concept illustrates how different global shapes could alter experience. Even in a flat universe, looping remains possible if topology, the way space is connected, is non-trivial. Geometry describes local curvature, while topology describes overall connectedness. A flat sheet can be folded and glued into a cylinder or torus without changing local geometry. In the same way, the universe might be flat, but topologically complex. It could possess dimensions that reconnect subtly, creating pathways that circle back. Detecting such topology requires identifying repeated patterns in distant galaxies or background radiation, a challenging endeavor. Why does flatness matter? One reason lies in the early universe. Inflation, a rapid period of expansion shortly after the beginning, predicts that space should appear extremely flat, just as the surface of a balloon appears flatter the more it inflates. If inflation occurred as theorized, it would stretch any initial curvature to near invisibility. Observations supporting flat geometry thus provide indirect evidence for that early burst of expansion. Flatness becomes not just a geometric measurement, but a clue about cosmic origins. As you let your thoughts wander across these immense ideas, consider the humility required to measure such vastness. We are small beings on a small planet, orbiting an ordinary star in one galaxy among billions. Yet by studying faint radiation and the motion of distant galaxies, we infer the shape of the entire cosmos. We measure triangles that span billions of light years. We analyze patterns imprinted when the universe was only hundreds of thousands of years old. Geometry, once a classroom exercise, becomes a tool for understanding existence itself. Whether infinite or finite, looping or boundless, the universe appears consistent and coherent on the largest scales. There is no evidence of edges or abrupt boundaries. No wall encloses the cosmos. Space simply continues, expanding and unfolding. If it loops, it does so gently and invisibly. If it stretches infinitely, it does so without fanfare. The shape of the universe is not dramatic in appearance. It is subtle, revealed only through careful measurement. Imagine drifting outward through space, beyond galaxies, beyond clusters, beyond the cosmic web. Would you eventually circle back? Would you continue forever? The answer depends on properties that may lie beyond our observable reach. The horizon limits certainty, yet within that horizon space behaves almost perfectly flat. Parallel light rays remain parallel. The angles of immense cosmic triangles sum as expected. Geometry appears steady and calm. There is something soothing about that steadiness. Despite its vastness and complexity, the universe follows consistent mathematical rules. Its geometry is not chaotic. It is precise and measurable. The same equations describing curvature near a star apply across billions of light years. Whether infinite or looping, space unfolds according to patterns we can discern. That reliability allows us to explore with confidence, even when imagination falters. As you settle into this thought, let the scale expand gently in your mind. A universe possibly infinite, possibly finite, yet unbounded, shaped by curvature too subtle to detect directly. Light, traveling across billions of years, tracing triangles across cosmic expanses, space itself bending or stretching quietly without edges or seams. The shape of the universe remains one of the deepest questions we can ask, not because it threatens us, but because it humbles us. Flat, curved, infinite. The evidence points toward flatness, yet the full story may extend beyond what we can see. Cosmic geometry defines how everything fits together, how distances grow, how light moves. And whether space loops back on itself or stretches without end, it does so with quiet consistency. The universe does not announce its shape loudly. It reveals it gradually through faint patterns and distant signals. In the end, the shape of the universe is less about boundaries and more about structure. It is about how space behaves at scales so vast they challenge comprehension. And as you imagine traveling endlessly outward, perhaps never reaching an edge, perhaps circling gently back, you may find comfort in the idea that the cosmos, however shaped, holds together seamlessly. There are no cracks in its geometry, no tears in its fabric. Only space expanding patiently, shaped by curvature so subtle that it feels almost perfectly flat beneath the mind's wandering gaze. When we look at a spiral galaxy, it appears graceful and serene. Arms of starlight curve outward from a glowing center, dust lanes tracing delicate patterns between bright clusters. From a distance, the structure seems stable, almost gentle. But beneath that calm appearance lies a puzzle that has unsettled astronomers for nearly a century. The stars in those outer arms are moving far too fast. According to the visible mass we can measure, the stars, the gas, the glowing dust, they should not be able to hold together. And yet they do. To understand why this is strange, imagine a carousel spinning in a playground. The outer horses must move faster than the inner ones to complete each circle in the same amount of time. If they spin too quickly, they would be flung outward unless something strong holds them in place. In galaxies, gravity plays that role. The combined mass of all stars and gas generates the gravitational pull that keeps everything orbiting the center. The expectation, based on classical mechanics, is straightforward. As you move farther from the galactic center, orbital speeds should decrease. The farther a star is from the bulk of the mass, the weaker the gravitational pull should be. But that is not what we observe. When astronomers began measuring the rotation speeds of stars in spiral galaxies in the mid-20th century, they found something unsettling. Instead of slowing down with distance, stars in the outer regions were moving at nearly the same speed as those much closer to the center. The rotation curves, graphs of speed versus distance, flattened out instead of declining. The outer stars were orbiting too fast to be explained by visible matter alone. If gravity came only from the stars and gas we can see, those outer regions should tear apart, yet galaxies remain intact. The implication is clear, but deeply mysterious. There must be more mass present than we can detect with light. Something invisible surrounds and permeates galaxies, adding gravitational pull without emitting or reflecting radiation. This unseen substance has been given a name that describes what we know about it and what we do not. It is called dark matter. Dark not because it is sinister, but because it does not interact with light in any measurable way. The evidence for dark matter does not come from a single observation. It emerges from multiple lines of inquiry, all pointing toward the same conclusion. Long before precise galactic rotation curves were measured, astronomers studying clusters of galaxies noticed a similar discrepancy. In the 1930s, Swiss astronomer Fritz Zwicky observed that galaxies within the Coma cluster were moving so rapidly that the cluster should disperse unless there was far more mass than visible stars accounted for. He referred to this missing mass as dunkle Materie, or dark matter. At the time, his claim received little attention. But decades later, with improved measurements, the pattern became undeniable. When we examine a galaxy cluster today, we see galaxies orbiting within it at speeds that suggest enormous gravitational influence. We also observe hot gas glowing in X-rays between galaxies. Even when we account for all of this visible matter, it is not enough. The cluster remains bound together because of additional mass we cannot see. Once again, gravity points to something hidden. Another powerful line of evidence comes from gravitational lensing. According to general relativity, mass bends space-time, and light follows those curves. When light from a distant galaxy passes near a massive object, such as a galaxy cluster, its path is distorted. The background galaxy appears stretched, magnified, or multiplied into arcs and rings. By measuring these distortions, astronomers can map the distribution of mass causing the bending. Time and again, the maps reveal more mass than luminous matter alone can account for. The gravitational lensing signal outlines vast halos of invisible material surrounding clusters and individual galaxies. We do not see dark matter itself. We see what it does. Imagine standing on a hill and watching tall grass ripple in the wind. You cannot see the wind directly, but the motion of the grass reveals its presence. In a similar way, we observe stars orbiting at unexpected speeds, galaxies moving within clusters, and light bending more strongly than visible matter permits. These motions are the grass. Dark matter is the wind. The prevailing picture suggests that every galaxy is embedded within a massive halo of dark matter. This halo extends far beyond the visible disk of stars, forming a roughly spherical envelope that outweighs luminous matter several times over. In the Milky Way, for example, the mass of dark matter is estimated to be about 5 times greater than that of all stars and gas combined. Without this halo, our galaxy's rotation would look entirely different. The outer stars would not remain in stable orbits. The structure we inhabit would not hold together as it does. Dark matter also plays a crucial role in cosmic history. After the universe became transparent and the first light traveled freely, tiny fluctuations in density began to grow. Ordinary matter, hydrogen and helium, interacted with radiation and remained somewhat smooth for a time. Dark matter, however, does not interact with light. It does not feel radiation pressure. As a result, it began clumping earlier and more efficiently. These dark matter clumps formed gravitational wells into which ordinary matter eventually fell. In this sense, dark matter acted as scaffolding for cosmic structure. It provided the invisible framework upon which galaxies assembled. Simulations of cosmic evolution support this idea vividly. When astrophysicists model the growth of structure in a universe containing dark matter, they reproduce the large-scale patterns we observe, a cosmic web of filaments connecting dense nodes of galaxies separated by vast voids. Without dark matter in the simulations, the structures form too slowly and too differently to match reality. The presence of this invisible component seems necessary to explain the universe's architecture. Yet for all this gravitational evidence, dark matter remains undetected in any direct sense. It does not emit light. It does not absorb or reflect photons. It does not appear to interact electromagnetically at all. If dark matter particles pass through you at this moment, and they likely do, you would not notice. They would drift silently, interacting only through gravity and perhaps through extremely weak forces yet to be confirmed. Physicists have proposed various candidates for what dark matter might be. One possibility is that it consists of new kinds of particles beyond the familiar protons, neutrons, and electrons. Weakly interacting massive particles, or WIMPs, have long been a leading candidate. These hypothetical particles would interact through gravity and possibly the weak nuclear force, but not through electromagnetism. Experiments deep underground, shielded from cosmic rays and background radiation, are designed to detect rare collisions between WIMPs and atomic nuclei. So far, those experiments have not yielded definitive results. Another possibility involves particles known as axions, light, elusive entities proposed to solve unrelated theoretical puzzles. Axions could be produced in enormous numbers in the early universe, contributing significant mass without interacting strongly with light. Specialized detectors attempt to convert axions into photons under strong magnetic fields, searching for faint signals that would reveal their presence. These searches continue with increasing sensitivity. More exotic proposals exist as well. Some scientists consider sterile neutrinos, primordial black holes, or entirely new hidden sectors of physics. Each hypothesis aims to explain how something invisible could account for so much gravitational influence. Yet despite decades of investigation, no candidate has been confirmed conclusively. Dark matter remains inferred rather than identified. This uncertainty can feel unsettling. How can most of the universe's matter be invisible and unknown? Estimates suggest that ordinary matter, the atoms forming stars, planets, and living beings, constitutes only about 5% of the universe's total energy content. Dark matter makes up roughly 27%. The remainder is attributed to dark energy, which drives accelerating expansion. In other words, everything we directly experience and observe with light is a minority component of reality. But there is a quiet beauty in this humility. The universe reveals itself gradually. We once believed the Milky Way contained all stars. Later we discovered other galaxies. Then we learned that most matter does not shine. Each step expanded our perspective. Dark matter does not diminish the cosmos. It deepens it. Imagine the Milky Way at night, its spiral arms arching across the sky. Beyond what you see lies an enormous halo, stretching far beyond the visible disk. That halo is not empty. It is filled with dark matter, forming a vast invisible skeleton supporting the luminous structure. Stars orbit within it, guided by gravitational currents shaped by something we cannot touch or see. We are embedded within that skeleton, moving through it quietly. The concept of an invisible framework holding galaxies together might once have seemed speculative. Today, it is part of mainstream cosmology, supported by independent evidence from galaxy rotations, cluster dynamics, gravitational lensing, and cosmic microwave background measurements. Each method converges on the same conclusion. There is more mass than meets the eye, and still, the substance remains elusive. We see its gravity, not the substance itself. As you let this idea settle, consider the difference between presence and visibility. Air surrounds you, yet you cannot see it directly. Gravity shapes your movement, yet it has no color or texture. Dark matter is similar, though far more mysterious. Its presence is revealed through motion and curvature. Its substance is hidden. Galaxies spin too fast. Clusters hold together too tightly. Light bends too strongly. These are not errors in observation. They are consistent signals pointing towards something unseen. The invisible skeleton of the universe exerts its influence silently, guiding structure from the earliest epochs to the present moment. If dark matter did not exist, the cosmos would look profoundly different. Galaxies might not form at all, or they would appear smaller and less stable. The cosmic web would lack its intricate filaments. The universe would be less structured, less complex. Dark matter's gravitational pull is not an incidental detail. It is foundational, and yet as vast as its influence may be, it does not glow. It does not sparkle in the night sky. It leaves no luminous trail. Its role is quiet, structural, persistent. In the end, dark matter invites patience. It reminds us that absence of light does not mean absence of reality. The universe contains layers beyond what our senses detect. We learn about them indirectly. Through careful measurement and thoughtful inference, we build detectors deep underground. We analyze distant arcs of lensed galaxies. We simulate cosmic evolution on supercomputers, all to glimpse the outline of something that refuses to shine. As you drift deeper into this thought, imagine the Milky Way suspended within its vast halo, spinning serenely. The outer stars move swiftly, yet remain bound. The galaxy holds together because of an invisible embrace. You are carried along within that motion, orbiting the center once every 200 million years, never noticing the unseen mass guiding your path. The universe has a skeleton made of darkness. We do not see its substance, we feel its gravity. And through that quiet pull, galaxies endure, structures form, and the cosmic story continues, steady, unseen, and profoundly real. For most of the 20th century, astronomers believed they understood the broad story of the universe's expansion. Ever since Edwin Hubble observed that distant galaxies are moving away from us, it became clear that space itself is stretching. The farther a galaxy lies from us, the faster it appears to recede. This observation led naturally to a simple expectation. If the universe began in a hot, dense state, and has been expanding ever since, then gravity, acting between all matter, should gradually slow that expansion down. The cosmos, filled with mass, should tug inward on itself. The rate of expansion might decrease over time, perhaps even halt and reverse in a distant future. That expectation seemed reasonable. Gravity pulls, it gathers, it resists outward motion. For decades, cosmologists debated whether there was enough matter in the universe to eventually stop the expansion entirely. If so, the cosmos might one day collapse in a fiery contraction, a scenario often called the Big Crunch. If not, expansion would continue forever, gradually slowing but never reversing. These were the two main possibilities considered for much of modern cosmology's early development. Then, in the late 1990s, something unexpected emerged. Two independent teams of astronomers were studying distant supernovae, exploding stars whose brightness can be used to measure cosmic distances. By observing how bright these supernovae appeared compared to how bright they should be, scientists could estimate how far away they were and how quickly the universe had been expanding when their light began its journey. The goal was to determine whether expansion was slowing down, as gravity suggested it should. Instead, the data revealed the opposite. The most distant supernovae were dimmer than expected. They were farther away than models predicted for a decelerating universe. The only consistent explanation was startling. The expansion of the universe is not slowing down. It is speeding up. Space is not merely stretching. It is stretching faster with time. This discovery transformed cosmology almost overnight. If gravity pulls inward, something else must be pushing outward. There must be a component of the universe that exerts a kind of repulsive effect on cosmic scales, counteracting gravity and driving acceleration. This unknown influence was given a name that captures both its significance and our ignorance: dark energy. Unlike dark matter, which clumps and forms halos around galaxies, dark energy appears smooth and evenly distributed. It does not gather into structures. It does not create filaments or clusters. Instead, it permeates space uniformly, acting not as a substance that pulls objects together, but as an energy intrinsic to space itself. As space expands, dark energy does not dilute in the same way matter does. Its density remains nearly constant. Even as the universe grows larger, this property is what makes it so powerful. In a universe filled only with matter, expansion slows over time because gravity's pull weakens outward motion. But in a universe containing dark energy with constant density, something different happens. As space expands, the total amount of dark energy increases because there is more space for it to inhabit. More volume means more dark energy overall. And because dark energy exerts a negative pressure, a kind of outward push, its influence grows stronger relative to matter. As the universe expands, in the early universe matter dominated, galaxies formed, structures assembled, gravity shaped the cosmic web. Dark energy was present, but its influence was negligible compared to the density of matter. Over billions of years, as space stretched and matter became more diffuse, dark energy's relative contribution grew. Around 5 billion years ago, it became the dominant component of the universe's energy budget. From that point onward, acceleration began to take control. The idea that empty space itself contains energy is not entirely new. Even in quantum physics, the vacuum is not truly empty. It seethes with fleeting particle-antiparticle pairs that appear and vanish in tiny fractions of time. These quantum fluctuations imply that space possesses intrinsic energy. Einstein himself introduced a term into his equations, called the cosmological constant, to allow for a static universe. After expansion was discovered, he reportedly referred to that addition as a mistake. Yet with the discovery of acceleration, the cosmological constant returned as a viable explanation. If dark energy is equivalent to a cosmological constant, it means that space has a fixed energy density that does not change over time. Every cubic meter of empty space contains a tiny amount of energy, and as the universe expands, more cubic meters come into existence. The total dark energy increases simply because space increases. This concept is difficult to grasp intuitively. We are accustomed to thinking of energy as something that comes from objects. Stars radiate energy, batteries store energy, motion carries energy. But dark energy appears to be woven into the fabric of space itself. It does not originate from galaxies or particles. It is intrinsic to emptiness. The acceleration it produces is subtle on small scales. Within galaxies, gravity dominates completely. The Milky Way is not being torn apart by expansion. Solar systems remain bound. Even clusters of galaxies stay intact because their gravitational attraction overwhelms dark energy locally. But on scales spanning hundreds of millions of light years, where gravity's grip weakens, acceleration becomes noticeable. Distant galaxies recede faster and faster as space between them expands. If you imagine placing two dots on a stretching rubber sheet, the distance between them increases as the sheet expands. If the stretching rate itself increases over time, the dots move apart more rapidly with each passing moment. This is the current state of the universe. Galaxies not gravitationally bound to one another are drifting apart at accelerating speeds. The farther away they are, the faster they recede. The long-term implications are profound. If acceleration continues indefinitely, distant galaxies will eventually move so far away that their light will never reach us. There is a cosmic horizon beyond which expansion carries objects away faster than light can bridge the growing gap. Over trillions of years, the observable universe will shrink in terms of accessible structure. Galaxies outside our local group will fade from view, redshifted beyond detectability. The night sky will grow emptier, not because stars have vanished, but because expansion has carried them beyond reach. This scenario leads to what is often called the heat death of the universe. In such a future, expansion continues forever. Stars exhaust their fuel and burn out. Matter becomes increasingly isolated. Black holes slowly evaporate over incomprehensible timescales. Eventually, the cosmos becomes a cold, dilute sea of particles and radiation spread thin across vast distances. No new structures form because everything is too far apart. The universe approaches maximum entropy, a state of uniform, quiet emptiness. However, dark energy's nature remains uncertain. While the cosmological constant is the simplest explanation, alternative models propose that dark energy might evolve over time. In some theories, it is represented by a dynamic field called quintessence, whose energy density changes slowly as the universe expands. If dark energy strengthens over time, acceleration could become even more dramatic, leading to a hypothetical Big Rip. In that scenario, expansion eventually becomes so extreme that galaxies, stars, planets, and even atoms are torn apart by the stretching of space. Conversely, if dark energy weakens or reverses, the future might look very different. Acceleration could slow, and gravity might regain dominance, potentially leading to contraction. Current observations suggest that dark energy behaves very much like a cosmological constant, remaining steady and unchanging. But our measurements, though precise, cannot yet rule out subtle variations. It is astonishing to realize that the fate of everything depends on something we do not fully understand. Dark energy comprises roughly 68% of the universe's total energy content. Ordinary matter, the atoms forming stars and life, makes up only a small fraction. Dark matter contributes more, but even that is overshadowed by dark energy's influence on cosmic scales. Most of reality is governed by components invisible to our senses, and yet, despite its dominance, dark energy reveals itself only through large-scale behavior. We do not detect it in laboratories. We do not isolate particles associated with it. We infer its presence from the motion of distant galaxies and the brightness of ancient supernovae. It is subtle and pervasive, not dramatic in any immediate way. There is something strangely peaceful about this idea. The universe is not exploding apart violently. The acceleration is gentle, measurable only across immense distances and timescales. Galaxies drift away slowly, imperceptibly within a human lifetime. The night sky looks stable. Constellations do not rearrange visibly. The silent expansion continues without noise or spectacle. Imagine standing beneath a clear sky, unaware that space itself is stretching between distant galaxies. Imagine knowing that with each passing second the universe becomes slightly larger, the distances between clusters growing ever so subtly. This growth does not disturb your world. It unfolds quietly, beyond direct perception. The cosmos is expanding faster than ever before, yet your immediate surroundings remain calm. As you let this thought settle, consider how extraordinary it is that we can measure such acceleration at all. By studying supernovae billions of light years away, by mapping patterns in the cosmic microwave background, by analyzing the distribution of galaxies, we piece together the story of expansion. We observe light that began its journey when the universe was half its current age and compare it to closer signals. From these comparisons, acceleration becomes clear. Dark energy may be the most enigmatic component of cosmology. It challenges intuition. It suggests that emptiness is not empty. It implies that space has properties independent of the objects within it. And it reminds us that even after centuries of scientific discovery, we are still uncovering fundamental aspects of reality. The silent expansion continues as you sit here, breathing, thinking, perhaps drifting toward rest. On cosmic scales, galaxies are separating more rapidly than they once did. Space itself stretches gently, carrying clusters apart. The fate of everything, whether quiet fading, dramatic tearing, or some unforeseen transformation, depends on the true nature of dark energy. For now, the evidence suggests a steady acceleration, a gradual drifting apart that will continue indefinitely. The universe is not racing toward collapse. It is unfolding outward, steadily and quietly. In that expansion, there is no urgency, only vast timescales and patient motion. Dark energy does not glow, it does not clump, it does not announce itself. Yet it shapes the future of the cosmos. It determines whether galaxies remain visible to one another or fade into isolation. It decides how cold and empty the far future becomes. As you imagine the cosmos stretching softly outward, let the scale of it calm your thoughts. The acceleration is immense in scope but gentle in effect. Space expands, galaxies drift. The universe grows larger with every passing moment. And though we do not know precisely what dark energy is, we know that it guides the ultimate trajectory of everything that exists, quietly, persistently, and without a sound. If you could step far beyond the Milky Way, beyond its spiral arms, beyond the neighboring galaxies of the local group, beyond even the dense clusters that anchor vast regions of space, you would begin to see something extraordinary. The universe, on its largest scales, is not arranged randomly. It is not an even scattering of galaxies floating aimlessly in all directions. Instead, it forms an immense and intricate pattern, a structure so vast that it spans hundreds of millions of light years. Galaxies gather along delicate strands, stretching across space like threads of light woven into an enormous tapestry. Between those threads lie immense empty regions, vast cosmic voids where galaxies are scarce, and distances feel almost unimaginable. This grand arrangement is known as the cosmic web. For centuries, humans imagined the universe as either chaotic or uniform. Early telescopes revealed scattered smudges of light, but it was difficult to discern any large-scale pattern. Only in the past few decades, with deep sky surveys mapping millions of galaxies, has the web-like structure become clear. When astronomers chart the positions of galaxies across vast distances and plot them in 3 dimensions, the result resembles a network. Dense nodes of galaxies connect through elongated filaments, forming a structure reminiscent of neural pathways, branching rivers, or even the delicate lattice of a spider's web stretched across unimaginable space. These filaments are not small. Each one can span hundreds of millions of light years. Along them lie clusters and superclusters, massive gatherings of galaxies bound together by gravity. At the intersections of multiple filaments sit the densest nodes, regions containing thousands of galaxies and enormous reservoirs of hot gas. Between the threads stretch voids so large that if you traveled through one, you might journey tens of millions of light years before encountering another significant galaxy. The cosmic web defines the universe's large-scale architecture. This arrangement did not appear suddenly. It emerged gradually from the subtle density fluctuations imprinted in the early universe. After the first light was released and the cosmos became transparent, tiny variations in matter density existed throughout space. Some regions were slightly denser than others. Gravity amplified these differences over billions of years. Dark matter, which doesn't interact with radiation, began clumping first. Ordinary matter followed, falling into the gravitational wells created by dark matter. Over time, these wells deepened and connected, forming elongated structures that stretched across the expanding cosmos. The role of dark matter in shaping the cosmic web cannot be overstated. Because it interacts primarily through gravity, dark matter forms vast halos and filaments that act as scaffolding for visible matter. Computer simulations of cosmic evolution show this clearly. When astrophysicists simulate a universe containing dark matter, the resulting structure mirrors what we observe, a network of threads and nodes, with galaxies forming along those dense pathways. If dark matter is removed from the simulation, the structure fails to match reality. The web dissolves into something far less intricate. The unseen forces of gravity and dark matter are responsible for weaving this enormous pattern. Imagine looking at a map of the universe where each galaxy is represented by a glowing point. When plotted on large scales, those points do not fill space evenly. They cluster along thin lines, forming vast interconnected strands. The density within these filaments is higher than average, but still incredibly sparse by earthly standards. Even in a dense filament, galaxies are separated by millions of light years. Yet compared to the emptiness of surrounding voids, these threads are bustling highways of matter. Within the filaments, galaxies move under the influence of gravity, gradually migrating toward nodes where clusters reside. Gas flows along these structures as well, streaming toward regions of higher density. Over cosmic time, these flows feed star formation within galaxies, providing fresh material for new generations of stars. The web is not static. It evolves, reshapes, and stretches as the universe expands. Filaments lengthen, nodes grow more massive, voids widen. The voids themselves are remarkable in their emptiness. Some span over 100 million light years in diameter. They are not entirely devoid of matter. There are faint galaxies within them, but compared to the filaments, they are sparse. These vast regions form the negative space of the cosmic web, emphasizing the interconnected strands that outline them. If you were to stand inside one of these voids and look outward, you would see galaxies only faintly clustered along distant boundaries, like islands at the edge of a dark sea. The discovery of the cosmic web reshaped our understanding of the universe's organization. It revealed that structure emerges naturally from simple gravitational laws acting over immense timescales. Starting from tiny fluctuations in the early radiation field, gravity pulled matter into sheets and filaments, forming a pattern sometimes described mathematically as a foam-like arrangement. The web's geometry arises not from design, but from the interplay of expansion, dark matter clumping, and the steady pull of gravity. There is something quietly elegant about this structure. It is both ordered and organic. The filaments curve and branch unpredictably, yet the overall pattern remains consistent across different regions of space. No central hub governs the entire network. Each node connects locally to its neighbors, forming a decentralized architecture. The web stretches in every direction, limited only by the observable horizon. When we speak of galaxies arranged like threads, we are describing a reality that is difficult to visualize from within. Our Milky Way lies within one such filament, part of a supercluster known as Laniakea. This vast region contains hundreds of thousands of galaxies, all drifting gradually toward a central gravitational basin. Beyond Laniakea lie other superclusters, connected by filaments across distances that defy intuitive comprehension. We inhabit a single strand in an immense network. Gravitational lensing studies reveal dark matter distributed along these filaments, confirming that the visible galaxies trace underlying invisible mass. Observations of hot gas-emitting X-rays show matter flowing into nodes where clusters grow ever more massive. Even the distribution of quasars and distant galaxies aligns with the filamentary pattern. The cosmic web is not an illusion of limited sampling. It is a persistent feature of large-scale reality. As the universe continues to expand under the influence of dark energy, the web evolves. Filaments stretch further apart. Nodes become more isolated from one another. In the far future, acceleration will dominate so strongly that regions of the web will drift beyond each other's observable horizons. The grand interconnected network will fragment into isolated islands, each surrounded by expanding emptiness. For now, however, the web remains intact and measurable. It is astonishing to consider that this immense structure arose from fluctuations so small they were nearly uniform. The early universe was smooth to 1 part in 100,000, yet those slight differences, amplified over billions of years, created a pattern spanning the cosmos. Complexity emerged not from chaos but from subtle variation, magnified patiently by gravity. The cosmic web also influences how galaxies form and evolve. Galaxies within dense filaments experience more frequent interactions and mergers. Clusters at nodes are crowded environments where gravitational encounters shape galactic morphology. In contrast, galaxies in voids often remain smaller and less disturbed, evolving in relative isolation. The environment within the web determines much of a galaxy's story. When astronomers map redshifts, measures of how much galaxy light has been stretched by expansion, they create three-dimensional surveys of the universe. These maps reveal walls of galaxies, vast arcs and clusters, outlining voids. The Sloan Great Wall, for example, is a colossal structure extending over 1 billion light-years. It is one of many such formations traced by galaxy surveys. Each discovery reinforces the idea that the universe's largest features are not spherical clusters alone, but extended filaments woven together. The metaphor of a web is fitting not only because of its appearance, but because of its function. A web distributes tension across threads. If one strand shifts, neighboring strands respond. In the cosmic web, gravitational influences ripple along filaments. Matter flows inward along these pathways. The structure is dynamic, responsive, and interconnected. Imagine drifting far above it all, looking down at a glowing network spanning unimaginable distances. Each luminous node represents thousands of galaxies. Each filament channels matter across cosmic expanses. The spaces between appear dark and quiet. There is no center, no edge, just an endless pattern repeating at scales beyond easy comprehension. The cosmic web challenges the notion of randomness. On small scales, the universe can seem chaotic, but zoomed outward, order emerges. Patterns appear from complexity. The arrangement of galaxies follows statistical rules shaped by initial conditions in gravitational physics. It is a testament to how simple laws, applied consistently over immense time, produce structures of breathtaking scale. As you let this image settle, imagine the Milky Way's position within one of these filaments. Our galaxy orbits within a network shaped by forces acting long before Earth formed. Dark matter flows along invisible strands, guiding the distribution of luminous matter. Gas streams toward clusters where new stars ignite. All of this unfolds slowly, almost imperceptibly from a human perspective. The cosmic web is not static architecture. It is ongoing evolution. Filaments thin and stretch. Nodes merge and grow. Voids expand as matter migrates toward denser regions. Over billions of years, the pattern shifts subtly, always governed by gravity and expansion. The unseen forces that shaped the early universe continue to guide its transformation. There is something calming in recognizing that even at the largest scales, the universe possesses structure. It is not a featureless expanse. It is organized, though not rigidly. It is connected, though not centralized. The web spans billions of light years, linking galaxies in threads of gravity and dark matter. Galaxies arranged like threads, vast filaments and nodes, structure shaped by unseen forces. This is the grand design of the cosmos, and within that design you exist in a small spiral galaxy orbiting quietly within one filament of an enormous network. The web stretches far beyond what you can see, yet its influence reaches you through gravity and motion. It is the silent framework of the universe, vast and intricate, woven from darkness and light across the deepest reaches of space. If the cosmic web is the grand architecture of the universe, then the voids are its vast and silent chambers. Between the glowing filaments and dense clusters lie enormous regions where galaxies are rare, sometimes separated by tens of millions of light years. These are not small gaps or modest pockets of emptiness. They are immense spherical expanses that can stretch across hundreds of millions of light years. Within them, matter thins to a whisper. Light from distant galaxies traces their boundaries like faint lanterns around the edges of a dark sea. These regions are known as cosmic voids, and they are among the largest structures in existence. When astronomers first began mapping galaxies in 3 dimensions, they expected to find clusters and superclusters. What they did not anticipate was how profoundly uneven the distribution would be. Galaxies were not scattered randomly. Instead, they gathered along vast walls and filaments, leaving behind cavernous spaces almost devoid of luminous matter. The discovery of these voids in the late 20th century reshaped our picture of the universe's large-scale structure. It revealed that emptiness itself is an essential feature of cosmic design. A cosmic void is not entirely empty. There are galaxies within it, but they are few and far between. Compared to the dense nodes of the cosmic web, where thousands of galaxies can cluster within a relatively small volume, voids contain only a small fraction of the average galactic density. In some regions, the density drops to less than 10% of the cosmic mean. If you were to travel through such a void, you might drift for millions of light years before encountering another substantial galaxy. The distances would feel staggering even by astronomical standards. One of the most famous examples is the Bootes void, discovered in 1981. Spanning roughly 250 million light years across, it is so vast that it could contain thousands of galaxies, yet only a handful reside within it. To grasp its scale, consider that the entire Milky Way galaxy is about 100,000 light years in diameter. The Bootes void is thousands of times larger. It is a region where matter seems to have stepped aside, leaving a near-empty volume in its place. These enormous voids formed naturally as part of the same gravitational processes that created filaments and clusters. In the early universe, density fluctuations existed everywhere. Regions slightly denser than average pulled in surrounding matter, becoming filaments and nodes. Regions slightly less dense lost matter to their surroundings. As matter flowed toward denser regions, underdense areas became emptier still. Over billions of years, these low-density regions expanded and deepened, forming the vast cavities we now observe. The process is subtle but relentless. Gravity does not merely gather matter into clusters, it also evacuates matter from voids. Imagine a landscape of hills and valleys. Rainwater flows downhill into valleys, leaving the peaks dry. In a similar way, matter flows from voids into filaments. The denser regions grow denser, the emptier regions grow emptier. The cosmic web sharpens its contrast, emphasizing both its luminous strands and its dark hollows. What would it be like to exist within a cosmic void? From within such a region, the sky would appear different. Galaxies would cluster along distant boundaries, faint and sparse. The night would feel deeper, more expansive. There would be fewer neighboring galaxies to interact with. Star formation might proceed more slowly, as less gas flows inward from surrounding structures. Galaxies inside voids often appear smaller and less evolved than their counterparts in crowded clusters. Voids are sometimes described as the quietest places in existence, not because sound travels there, space remains silent everywhere, but because gravitational interactions are minimal. In clusters, galaxies collide and merge. Gas is heated to millions of degrees. Black holes feed actively at galactic centers. In voids, such dramatic encounters are rare. Galaxies drift in relative isolation, evolving gently over cosmic time. The pace of change is slower, the environment calmer. The expansion of the universe influences voids more dramatically than it does dense regions. Because voids contain less matter, gravity exerts less inward pull. As dark energy drives acceleration, voids expand faster than average. Their boundaries stretch outward, enlarging the empty regions between filaments. Over time, voids may come to dominate the cosmic landscape. The web's filaments could become thinner and more isolated as acceleration continues. Studying voids provides insight into fundamental cosmology. Their size distribution and evolution depend sensitively on the amount of dark matter and dark energy in the universe. By mapping voids across vast surveys, astronomers test theoretical models of structure formation. Voids act as laboratories for understanding gravity itself. Some alternative theories of gravity predict different behavior within underdense regions compared to dense clusters. Observing how galaxies move inside voids helps constrain such ideas. Voids also influence the cosmic microwave background through subtle effects. As light from the early universe passes through large voids on its journey to us, it can gain or lose energy depending on how space is expanding. This phenomenon, known as the integrated Sachs-Wolf effect, leaves faint imprints on the background radiation. By correlating void positions with microwave fluctuations, scientists further probe the role of dark energy in shaping cosmic evolution. Despite their emptiness, voids are not devoid of interest. Within them reside delicate structures, thin filaments and isolated galaxies that trace subtle flows of matter. Some void galaxies appear unusually blue, indicating ongoing star formation. Without frequent mergers to disrupt them, they may preserve features lost in denser environments. Studying such galaxies reveals how isolation influences evolution. The sheer scale of voids challenges imagination. A region spanning 200 million light-years means that even light, traveling at its maximum speed, requires 200 million years to cross it. Entire epochs of Earth's history fit comfortably within that span. While dinosaurs roamed and vanished, light could barely traverse a single cosmic void. These distances dwarf human experience, stretching thought to its limits. Yet voids are not anomalies. They occupy a substantial fraction of the universe's volume. While most galaxies reside in filaments and clusters, most of space by volume consists of underdense regions. The universe, in terms of sheer emptiness, is dominated by voids. The luminous strands are like delicate tracings around immense expanses of darkness. There is a quiet beauty in that asymmetry. The web's filaments glow with countless galaxies, yet they thread through oceans of emptiness. The balance between presence and absence defines cosmic structure. Without voids, there would be no web. The contrast gives shape to the universe's architecture. Imagine drifting through one of these voids. There would be no nearby galaxies dominating the sky. The nearest large cluster might be tens of millions of light years away, visible only as a faint gathering of distant lights. The sense of isolation would be profound. And yet even there, gravity from surrounding structures would gently guide motion. The void is not cut off from the rest of the cosmos. It is part of the web's pattern, shaped by the same forces that shape everything else. Over billions of years, voids grow larger as matter continues migrating outward. They merge with neighboring voids, forming supervoids that span even greater distances. These enormous regions influence cosmic flows, subtly redirecting galaxy motions along their boundaries. In some cases, supervoids align with large cold spots in the cosmic microwave background, prompting investigations into whether such alignments are coincidental or significant. The idea of emptiness on such scales may evoke a sense of loneliness. Yet voids are not barren wastelands. They are integral components of structure. They define the space in which galaxies arrange themselves. They create the contrast necessary for filaments to stand out. They allow gravity to sculpt complexity by redistributing matter over time. From a philosophical perspective, voids remind us that absence can be as important as presence. The universe's design includes immense spaces where little happens, where interactions are rare. These quiet regions balance the dynamism of clusters and star-forming galaxies. The cosmic story unfolds not only in luminous bursts but also in silent expanses. As dark energy continues driving acceleration, the role of voids becomes even more significant. Their expansion will outpace that of denser regions, further isolating clusters from one another. In the distant future, observers in a galaxy bound within a cluster may see little beyond their local group. Surrounding voids will have stretched so extensively that distant filaments slip beyond visibility. The universe's large-scale network will fragment into isolated islands, separated by expanding emptiness. For now, though, the web remains connected, and voids serve as its vast negative spaces. They are millions of light years across, the quietest places in existence. They stretch beyond intuitive comprehension, defining the cosmic landscape through absence. Within their depths, galaxies drift gently, unhurried by crowded interactions. This silence there is not the absence of physics, but the absence of density. As you imagine the cosmic web from afar, let your mind trace the glowing filaments and then rest in the dark spaces between them. Those immense voids hold no spectacular fireworks, no crowded galactic dances. They are expansive, calm, patient. The universe contains both intricate threads and vast emptiness, both luminous clusters and silent chambers. In that balance lies the grandeur of cosmic structure. Enormous empty regions millions of light years across shape the universe as profoundly as its brightest stars. The quietest places in existence are not small or insignificant. They are monumental in scale. And as the universe continues its silent expansion, those voids will grow larger still, stretching the web's threads ever farther apart in a vast and patient unfolding. Somewhere in the quiet depths of nearly every large galaxy, there is a region where gravity becomes so intense that space and time themselves begin to behave differently. Not metaphorically, not poetically, literally. There are places in the universe where time slows, where light bends inward, where the geometry of reality curves so steeply that escape becomes impossible. These places are called black holes, and they are among the most extraordinary predictions of modern physics. A black hole does not begin as a hole at all. It begins as a star, a massive star, far larger than our sun, spends millions of years fusing hydrogen into helium, helium into heavier elements, balancing the inward pull of gravity with the outward pressure of nuclear fusion. For most of its life, this balance holds. But when the fuel runs out, pressure drops. Gravity, which has always been there, waiting patiently, takes control. The core collapses inward with tremendous force. If the star is massive enough, nothing can stop the collapse. The core compresses beyond neutron degeneracy pressure, beyond any known form of stable matter. Gravity continues pulling inward until a boundary forms. an invisible surface known as the event horizon. The event horizon is not a solid shell. It is not made of matter. It is a threshold in space-time. Once crossed, nothing, not even light, can return. Escape velocity exceeds the speed of light, and because nothing can travel faster than light, escape becomes impossible. From outside, the event horizon appears as a dark sphere, absorbing all radiation that passes too close. But what makes it remarkable is not simply its darkness, it is what happens to space-time itself in its vicinity. According to Einstein's general theory of relativity, mass tells space-time how to curve, and curved space-time tells matter how to move. Around Earth, this curvature is gentle. Around the Sun, it is stronger. Around a black hole, it becomes extreme. Space-time bends inward dramatically, forming a gravitational well so deep that trajectories spiral toward the center. Light passing near a black hole does not travel in straight lines. It arcs and loops, sometimes circling the black hole before escaping. In some cases, light can orbit entirely, forming what are known as photon spheres, regions where gravity bends light into circular paths. Time itself is affected by this curvature. The stronger the gravity, the slower time passes relative to distant observers. This effect, called gravitational time dilation, occurs around any massive object, but near a black hole, it becomes profound. Imagine a clock slowly descending toward the event horizon. To an observer far away, that clock appears to tick more and more slowly. As it approaches the horizon, its ticking stretches out, becoming sluggish. From the outside perspective, it never quite crosses the horizon. It appears frozen in time, redshifted and dimming until it fades from view. Yet from the perspective of the clock itself, if we imagine it could experience anything, nothing unusual happens at the horizon. It crosses without noticing a sharp boundary. This difference in perspective is one of the most fascinating aspects of black hole physics. Reality depends on where you stand. From far away, time nearly stops at the horizon. From close up, time continues forward normally. Both descriptions are correct within their frames of reference. Inside the event horizon lies the singularity, a region where our current understanding of physics breaks down. General relativity predicts that density becomes infinite, and space-time curvature becomes infinite as well. These infinities signal that our theory is incomplete. Quantum mechanics, which governs the microscopic world, cannot reconcile easily with the classical description of gravity in such extreme conditions. The singularity marks the boundary of knowledge. We cannot describe what truly occurs there because our equations cease to function reliably. Black holes are not merely theoretical curiosities. They are observed throughout the universe. Stellar mass black holes form from collapsing stars and typically contain several times the mass of the Sun. Supermassive black holes reside at the centers of galaxies, including our own Milky Way. Sagittarius A, the black hole at our galaxy's core, contains about 4 million solar masses. Its gravitational influence shapes the motion of nearby stars, whose orbits provide direct evidence of its presence. Despite their reputation, black holes are not cosmic vacuum cleaners indiscriminately swallowing everything nearby. If our Sun were magically replaced by a black hole of equal mass, Earth would continue orbiting normally. The gravitational pull would be unchanged at that distance. Black holes exert the same gravitational influence as any object of equal mass. What makes them extraordinary is not how far their gravity reaches, but how intense it becomes near the event horizon. The region just outside a black hole can be astonishingly bright. Gas and dust falling toward the horizon form an accretion disk, heated to extreme temperatures by friction and gravitational compression. These disks can outshine entire galaxies, emitting X-rays and other high-energy radiation. Some black holes launch jets of plasma extending thousands of light years, powered by magnetic fields interacting with the spinning event horizon. These jets sculpt interstellar environments and influence galaxy evolution. Yet beyond their dramatic astrophysical roles lies a deeper puzzle, the information paradox. In classical physics, information about a system's state is never truly destroyed. Quantum mechanics preserves information through the evolution of wave functions. If you know the exact state of a system at one time, You can, in principle, determine its past and future states. But black holes challenge this principle. In the 1970s, physicist Stephen Hawking made a groundbreaking discovery. By combining quantum field theory with general relativity, he showed that black holes are not entirely black. Quantum fluctuations near the event horizon allow particle-antiparticle pairs to form briefly. If one particle falls into the black hole while the other escapes, the escaping particle appears as radiation emitted by the black hole. Over time, this Hawking radiation causes the black hole to lose mass. Eventually, if it does not gain new material, it could evaporate entirely. Here is where the paradox emerges. Hawking radiation appears thermal. It carries no detailed information about what fell into the black hole. If a black hole forms from collapsing matter containing complex information and later evaporates completely into radiation that contains none of that information, then information has been destroyed. This contradicts a central tenet of quantum mechanics, which insists that information must be conserved. The information paradox remains one of the deepest unsolved problems in theoretical physics. Various solutions have been proposed. Some suggest that information is subtly encoded within Hawking radiation through quantum entanglement. Others propose that black holes do not truly erase information but store it in ways we do not yet understand. The holographic principle, inspired partly by black hole thermodynamics, suggests that all information within a volume of space may be encoded on its boundary surface. According to this idea, the event horizon could store information in two-dimensional form, preserving it even as the black hole evaporates. Another proposal involves firewalls, hypothetical high-energy barriers at the event horizon that would destroy in falling matter, resolving the paradox at the cost of violating general relativity's equivalence principle. The debate continues, and no consensus has been reached. Black holes thus sit at the intersection of gravity and quantum mechanics, exposing the limits of both theories. There is something quietly humbling about this. Black holes are not just astrophysical objects, they are laboratories for fundamental physics. They reveal that our understanding of reality remains incomplete. Where space-time bends most sharply, where time slows and light curves inward, our equations falter. The universe reminds us that mystery persists even in the age of precision measurement. Imagine approaching a black hole from a safe distance. The stars behind it would appear distorted, bent around the dark silhouette. Closer still, time would slow relative to distant observers. Signals you send outward would stretch, their wavelengths lengthening as gravity redshifts them. At the horizon, light cannot escape. Beyond it, all paths lead inward. And yet, black holes are not monsters lurking in space. They are natural consequences of stellar evolution and gravitational law. They shape galaxies, regulate star formation, and drive energetic phenomena. They are part of the cosmic ecosystem. Time slows near them. Space-time bends inward. Information itself becomes a subject of debate. The event horizon marks a boundary, not only in space but in knowledge. Black holes invite us to contemplate the structure of reality at its most extreme. They challenge intuition and theory alike. As you let your thoughts settle, imagine the immense gravity at the center of a galaxy, bending light into arcs, stretching time into languid flow. Imagine the event horizon as a quiet threshold, invisible yet absolute. Beyond it lies a region from which no signal returns. Outside it, stars orbit, gas glows, and the universe continues expanding. In the vastness of the cosmos, black holes are points of intense inward pull amid the outward drift of dark energy. They represent concentration within expansion, collapse within growth. They are reminders that the universe contains both extremes and balances, and in those places where gravity reigns supreme, where space-time curves steeply and time slows almost to stillness, we find not only astrophysical marvels, but also profound questions. Questions about information, about the unity of physics, about what lies beyond the horizon of understanding. Black holes are not merely dark. They are luminous with mystery, bending reality inward and inviting us to look deeper still. At the center of nearly every large galaxy in the observable universe, there is something immense and silent, not a cluster of stars, not a glowing cloud of gas, but a gravitational anchor so powerful that entire stellar systems orbit its presence. These are supermassive black holes, cosmic giants containing millions or even billions of times the mass of our Sun. They do not shine on their own, yet their influence shapes galaxies across unimaginable distances. Quietly, persistently, they sit at the heart of structure itself. For much of human history, we did not know they existed. The idea that something invisible could reside at the center of a galaxy seemed speculative at best. But over the last several decades, careful observation has made the case undeniable. In our own Milky Way, astronomers tracked the motion of stars near the galactic center for years, watching them loop around an unseen mass. These stars move at extraordinary speeds, completing tight elliptical orbits around a dark region known as Sagittarius A*. The only explanation consistent with those velocities and trajectories is a compact object containing about 4 million solar masses packed into a region smaller than our solar system. That object is a supermassive black hole. And the Milky Way is not unique. Observations of other galaxies reveal similar behavior. Stars and gas near galactic centers orbit something invisible yet massive. In some galaxies, this central object weighs hundreds of millions or even billions of solar masses. The galaxy Messier 87, for example, hosts a black hole weighing about 6.5 billion times the mass of the Sun. In 2019, astronomers captured the first direct image of a black hole's shadow in M87, revealing the bright ring of hot gas swirling around its event horizon. That image was not merely symbolic. It was confirmation that these gravitational giants are real and common. In fact, current evidence suggests that nearly every large galaxy contains a supermassive black hole at its core. From massive elliptical galaxies to spiral galaxies like our own, the pattern holds. This raises a profound question. Why are they everywhere? How did such enormous objects form so early in cosmic history? And why do they appear to be intimately connected with the galaxies that surround them? To understand their significance, we must consider their scale. A stellar mass black hole forms from the collapse of a massive star and may contain a few times the Sun's mass. A supermassive black hole, by contrast, can weigh millions to billions of solar masses. That difference is staggering. It is not simply a larger version of the same thing. The formation mechanisms must have been far more dramatic and efficient. One of the mysteries surrounding supermassive black holes is how early they appeared. Observations of distant quasars, extremely luminous galactic centers powered by actively feeding black holes, show that some supermassive black holes already existed less than 1 billion years after the Big Bang. That is astonishingly early in cosmic history. The universe had barely begun forming galaxies, yet enormous black holes were already in place, consuming gas and shining brightly across vast distances. Quasars are among the brightest objects in the universe. When gas falls toward a supermassive black hole, it forms an accretion disk that heats to extraordinary temperatures. The disk radiates across the electromagnetic spectrum, sometimes outshining the entire galaxy that hosts it. In some cases, twin jets of charged particles shoot outward at near light speed, extending far beyond the galaxy's boundaries. These energetic phenomena are powered by gravity alone, by matter spiraling into the abyss. The existence of such early quasars implies that supermassive black holes must have formed quickly. But how? One possibility is that they began as seed black holes formed from the first generation of massive stars. These early stars, sometimes called population 3 stars, were likely enormous, perhaps hundreds of times the mass of the Sun. When they collapsed, they may have left behind black holes tens or hundreds of solar masses. Over time, through mergers and rapid accretion of gas, these seeds could have grown into supermassive giants. Yet this process may not be fast enough to explain the most massive early quasars. Some black holes observed in the early universe appear to have reached 1 billion solar masses in less than 1 billion years. Growing from a small seed to such enormous mass would require sustained, nearly uninterrupted feeding at the maximum theoretical rate allowed by physics. That seems challenging, though not impossible. Another possibility is that supermassive black holes formed directly from the collapse of enormous gas clouds in the early universe. In regions where cooling processes prevented fragmentation into smaller stars, Vast clouds of primordial gas might have collapsed straight into massive black holes containing tens of thousands of solar masses. These direct collapse black holes would have provided much larger seeds, accelerating the growth process. There is also the idea that dense clusters of stars in early galaxies may have merged and collapsed into intermediate mass black holes, which then grew further. Each of these scenarios is actively studied, and none has yet been definitively confirmed. What is clear is that supermassive black holes formed early and grew alongside galaxies. This brings us to another remarkable discovery. The mass of a galaxy's central black hole correlates strongly with properties of the galaxy itself, particularly the mass of its central bulge and the velocity dispersion of its stars. This relationship, known as the M-sigma relation, suggests a deep connection between galaxy formation and black hole growth. Somehow, the evolution of the galaxy and the evolution of its central black hole are intertwined. How can something so small in size compared to the galaxy influence it so profoundly? A supermassive black hole's event horizon may be smaller than our solar system, while the galaxy spans tens of thousands of light years. Yet the energy released as matter falls into the black hole can regulate star formation across the entire galaxy. When the black hole is actively feeding, it can produce powerful winds and jets that heat surrounding gas, or even expel it from the galaxy's core. This feedback process can limit the supply of cold gas available for new stars, effectively controlling the galaxy's growth. In this way, supermassive black holes act not merely as passive anchors but as regulators. They shape their host galaxies through cycles of activity and dormancy. During quasar phases, they blaze with radiation and drive energetic outflows. During quieter periods, they sit nearly invisible, influencing only the immediate motions of nearby stars. The question of why they are everywhere remains one of cosmic architecture. Did galaxies form first, with black holes growing inside them? Or did black holes form first, seeding galaxy formation around them? Evidence suggests that both processes may have occurred together. In the early universe, dark matter halos provided gravitational wells where gas could collect. Within those halos, conditions may have allowed rapid black hole formation. As galaxies assembled around them, the central black holes grew in tandem. It is possible that supermassive black holes are not accidents of galactic evolution, but essential components. Without them, galaxies might look different. Star formation histories could diverge. The large-scale structure of the cosmos might shift subtly. Their ubiquity implies necessity. Even smaller galaxies, including dwarf galaxies, sometimes host intermediate mass black holes, hinting that the process is widespread across scales. Though not every small galaxy has been confirmed to contain one, the trend suggests that black hole formation is a natural outcome of galaxy assembly. From a distance, a supermassive black hole is invisible unless actively feeding. But its gravitational influence is always present. Stars orbit in elongated paths near the center. Gas clouds swirl and sometimes plunge inward. The galaxy's core feels anchored, stabilized by an immense mass concentrated in a tiny volume. Imagine the early universe only a few 100 million years old. Gas clouds collapse, stars ignite, galaxies begin to form. In the dense cores of these newborn systems, black holes emerge and grow rapidly, shaping their surroundings. Over billions of years, galaxies merge with one another, and their central black holes spiral inward, eventually colliding and combining in titanic events that release gravitational waves rippling across space-time. The cosmic web itself becomes a network of galaxies, each with a dark heart. The fact that nearly every galaxy hosts one suggests a universal process at work. Gravity, gas dynamics, dark matter, and cosmic expansion all conspire to produce these central giants. They are not rare anomalies but common features. As the universe ages and star formation slows, many supermassive black holes become quieter. They still sit at the centers of galaxies, but without abundant gas to feed on. They emit little radiation. Our own Sagittarius A is relatively calm compared to active quasars. It consumes small amounts of gas and occasionally flares, but for the most part it remains subdued. yet its presence defines the orbits of nearby stars. It anchors the Milky Way's core. It is part of the galaxy's identity, woven into its structure. Why are they everywhere? Because the same forces that shaped galaxies, gravity, collapse, and cosmic evolution, naturally create them. Because early conditions allowed rapid growth. Because feedback between black holes and galaxies links their fates. Because in the vast interplay of matter and energy, concentrated mass at the center becomes almost inevitable. Supermassive black holes are paradoxical. They are points of extreme collapse within an expanding universe. They are engines of brilliant radiation and yet fundamentally dark. They are small compared to galaxies, yet enormous compared to stars. They formed early, persisted through mergers and transformations, and now sit at the centers of nearly every galactic system we observe. As you imagine the Milky Way stretching across the night sky, remember that at its center lies a region where gravity reigns supreme. Millions of solar masses compressed into a space smaller than the orbit of Mercury. Invisible, yet decisive. Quiet, yet powerful. And across the universe, in galaxy after galaxy, similar giants reside. Silent hearts beating slowly in the depths of cosmic time. Every galaxy has one. They formed early in cosmic history, and their near-universal presence tells us that they are not anomalies but foundational features of the cosmos itself. When a massive star reaches the end of its life, it does not go quietly. For millions of years it has balanced gravity with nuclear fusion, fusing lighter elements into heavier ones in a brilliant act of equilibrium. But eventually the fuel runs out, fusion slows, pressure drops. Gravity, which has patiently waited at the edge of every reaction, suddenly takes control. The outer layers collapse inward, rebound, and explode outward in a supernova so luminous it can briefly outshine an entire galaxy. What remains at the core depends on the star's original mass. For some, the collapse continues into a black hole, but for others, something different forms, something smaller than a city, yet heavier than a star. A neutron star. A neutron star is what happens when matter is compressed beyond ordinary imagination, but not quite beyond all limits. During collapse, electrons and protons are forced together under crushing pressure, merging into neutrons. The core becomes a single, vast atomic nucleus, bound not by chemical forces but by the strong nuclear force itself. The result is an object typically about 20 kilometers across, yet containing more mass than our Sun. Picture that scale for a moment. A sphere no larger than a small city, holding more material than all the planets, moons, and asteroids in our solar system combined. The density inside such an object defies everyday intuition. A teaspoon of neutron star matter would weigh billions of tons on Earth, comparable to the mass of a mountain compressed into something that could rest on your palm. Of course, no container could hold it. The moment that matter left the star's gravitational embrace, it would decompress explosively. The immense gravity of the neutron star is what keeps it in that tightly bound state. Gravity at the surface of a neutron star is extraordinary. If you stood upon it, assuming such a thing were physically possible, you would weigh trillions of times more than you do on Earth. The curvature of space-time near its surface is so strong that light bends noticeably. Photons emitted from the far side of the star can curve around toward an observer, allowing more than half the surface to be visible at once. Time itself runs more slowly there, though not as dramatically as near a black hole. Neutron stars occupy a boundary region of physics where gravity and nuclear forces engage in a delicate balance. Inside, conditions are stranger still. The outer crust consists of tightly packed nuclei embedded in a sea of electrons. Deeper down, the pressure forces nuclei into unusual configurations, sometimes described as nuclear pasta, because of the shapes theorized. Sheets and filaments of nuclear matter resembling lasagna or spaghetti on microscopic scales. Deeper still, neutrons flow freely in a superfluid state, moving without friction. The core may contain exotic forms of matter, perhaps hyperons or even quark matter. Though this remains uncertain, neutron stars are natural laboratories for extreme physics, places where densities exceed those of atomic nuclei and familiar matter transitions into unfamiliar phases. Yet neutron stars are not only remarkable for their density, Many of them spin rapidly, conserving angular momentum from the original star's collapse. When a large star shrinks to the size of a city, its rotation speeds up dramatically, like a spinning skater pulling in her arms. Some neutron stars rotate several times per second. Others spin hundreds of times each second. These rapidly spinning neutron stars, combined with intense magnetic fields, create one of the universe's most mesmerizing phenomena, pulsars. A pulsar is a rotating neutron star that emits beams of electromagnetic radiation from its magnetic poles. The magnetic axis of the star is often misaligned with its rotational axis. As the star spins, these beams sweep through space like lighthouse beams. If Earth lies in the path of one of these sweeping beams, we observe regular pulses of radiation, arriving with astonishing precision. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish. The signal appeared as a series of radio pulses so regular that it briefly earned the nickname LGM for Little Green Men, before its natural origin was understood. The precision of pulsars is extraordinary. Some rotate with such stability that their pulses rival atomic clocks in regularity. Over years of observation, their timing can be predicted with incredible accuracy. Tiny deviations in pulse arrival times reveal subtle effects: gravitational waves passing through space, planets orbiting the pulsar, or interactions with companion stars. Pulsars have become tools for testing fundamental physics, including general relativity. Magnetic fields around neutron stars are among the strongest known in the universe. While Earth's magnetic field is gentle and protective, a neutron star's field can be trillions of times stronger. These fields channel charged particles along magnetic lines, accelerating them to near light speeds and generating beams of radiation across the electromagnetic spectrum. Some neutron stars, known as magnetars, possess magnetic fields so intense they can crack the star's crust, producing bursts of high-energy radiation detectable across the galaxy. The life of a neutron star is quieter than that of its progenitor, yet still dynamic. Isolated neutron stars gradually cool and slow their rotation over millions of years. Their pulses become weaker. But in binary systems, interactions with companion stars can spin them back up. Matter falling from a companion transfers angular momentum, increasing the neutron star's rotation rate. These millisecond pulsars spin hundreds of times per second, some completing a rotation in less than 2 milliseconds. Their stability makes them exceptional cosmic timekeepers. Neutron stars also collide. When two orbit each other in a binary system, they gradually lose energy through gravitational radiation, spiraling closer over time. Eventually, they merge in a violent event known as a kilonova. Such collisions produce gravitational waves detectable across vast distances and create heavy elements like gold and platinum through rapid neutron capture processes. The gold in your jewelry may have formed in such a collision billions of years ago, forged in the merger of two neutron stars. The existence of neutron stars demonstrates the layered complexity of stellar evolution. Stars are not simply lights in the sky, they are engines of transformation. Massive stars live quickly and die dramatically, leaving behind remnants that compress matter into extraordinary forms. These remnants persist long after the original star has faded. From a distance, a neutron star appears unremarkable, just another point of radiation, but its compactness makes it unique. Its mass, squeezed into such a small volume, produces a gravitational field that warps space-time noticeably. Its rapid rotation and intense magnetism generate beams detectable across interstellar space. It is at once small and immense, subtle and extreme. Imagine drifting near a pulsar in the quiet depths of space. With each rotation, beams sweep outward rhythmically. If you could see radio waves as visible light, you would witness steady flashes marking the star's spin. The pulses would feel almost mechanical in their precision, yet they arise from natural processes: conservation of angular momentum, magnetic alignment, particle acceleration. The interior remains largely hidden from direct observation. We infer its composition from mass measurements, cooling rates, and theoretical models. Yet the uncertainty itself is part of the fascination. Neutron stars sit at a threshold where nuclear physics, quantum mechanics, and gravity intersect. They challenge our understanding of matter under extreme conditions. The phrase, "a teaspoon weighing billions of tons," captures only part of the wonder. It conveys density, but not the intricate physics that permits such density. It does not describe the superfluid neutrons flowing frictionlessly in the interior, or the magnetic storms erupting from the surface, or the gravitational waves emitted during mergers. Neutron stars are not static lumps of compressed matter. They are dynamic objects participating in cosmic evolution. They also provide a bridge between ordinary stars and black holes, increase the mass slightly beyond the neutron degeneracy limit, and gravity overwhelms even the strong nuclear force. The object collapses further, forming a black hole. Neutron stars therefore represent a delicate balance, gravity pushing inward, nuclear forces resisting collapse. They are the last stable configuration before space-time itself folds inward completely. In the broader tapestry of the universe, neutron stars and pulsars are rare compared to ordinary stars, yet numerous enough to populate galaxies. Thousands have been detected in the Milky Way alone, and many more likely remain unseen. Each one is a testament to stellar life cycles and the interplay of fundamental forces. As you consider their existence, imagine the compression required to turn a star into a sphere 20 kilometers wide. Imagine matter packed so tightly that atomic structure dissolves into a sea of neutrons. Imagine a rotating beacon sweeping through space with clock-like precision. These are not abstractions. They are real, observable phenomena scattered across our galaxy. The universe contains expanses of emptiness and filaments of galaxies, supermassive black holes anchoring spiral arms, and within those galaxies neutron stars spinning steadily. They represent extremes of density and magnetism, laboratories for physics beyond terrestrial reach. In the stillness of space, a pulsar's rhythm continues, flash after flash, rotation after rotation, marking time across cosmic distances. Matter compressed beyond imagination, cosmic lighthouses sweeping beams through darkness, a teaspoon weighing billions of tons. These are not poetic exaggerations, but physical realities unfolding quietly in the vast and patient universe. Among the many strange objects scattered across the universe, there are a few that seem almost excessive in their intensity. If neutron stars are already extreme, dense beyond imagination, spinning rapidly, bending space-time around them, then magnetars are neutron stars taken to a further edge. They are rare, short-lived by cosmic standards, and capable of unleashing energies that momentarily outshine entire galaxies. At their core lies a single defining feature, the strongest magnetic fields known in the universe. To understand a magnetar, it helps to begin with a neutron star. When a massive star collapses and its core compresses into a sphere roughly 20 kilometers wide, its rotation accelerates and its magnetic field intensifies dramatically. Conservation of angular momentum and magnetic flux ensures that what was once a modest stellar magnetic field becomes concentrated into something vastly stronger. In most neutron stars, this field is already trillions of times stronger than Earth's. But in rare cases, the magnetic amplification goes even further. The result is a magnetar. A typical magnetar's magnetic field can reach around 10^14 to 10^15 Gauss. For comparison, Earth's magnetic field is about half a Gauss. The strongest steady magnetic fields humans have generated in laboratories measure in the tens of thousands of Gauss. A magnetar's field exceeds that by a factor of trillions. It is so intense that it dominates the physics of the surrounding space. Within 1,000 kilometers, its influence is overwhelming. Within a few 100,000 kilometers, it remains profoundly significant. What does such a magnetic field do? It does not merely guide compass needles or shape auroras. It reshapes matter itself. In fields of this magnitude, atoms become distorted. The electron clouds that normally orbit atomic nuclei in spherical patterns are squeezed into elongated shapes, stretched along magnetic field lines. Chemical behavior changes. Vacuum itself becomes birefringent, meaning light traveling through the region behaves as though passing through a crystal, splitting into different polarization modes. These are not metaphorical distortions, but physical consequences of quantum electrodynamics operating under extreme conditions. Near the surface of a magnetar, the field is so strong that it can pull apart molecules. It can strip electrons from atoms at distances far beyond what gravity alone would accomplish. If a human somehow approached within a few thousand kilometers, a purely hypothetical scenario, the magnetic forces could disrupt neural signals and molecular bonds long before gravity or radiation had their effect. The environment around a magnetar is not merely hostile. It is fundamentally altered by magnetism. Magnetars are also unstable. The immense magnetic field stores vast amounts of energy within the star's crust and interior. Over time, that field can twist and stress the crust, building tension like tectonic plates under strain. When the crust yields, it cracks in what is often described as a starquake. The sudden rearrangement of magnetic field lines releases enormous bursts of high-energy radiation, X-rays and gamma rays that travel across the galaxy. These outbursts can be brief yet astonishingly powerful. In 2004, a magnetar known as SGR 180620 emitted a giant flare so intense that it briefly affected Earth's ionosphere, despite originating about 50,000 light-years away. For a fraction of a second, it released more energy than the sun emits in hundreds of thousands of years. The event demonstrated just how potent these objects can be. Unlike typical pulsars, which emit steady beams of radiation due to rotation and magnetic alignment, magnetars shine primarily because of magnetic decay. Their fields gradually unwind and dissipate energy over thousands to tens of thousands of years. This makes them relatively young in cosmic terms. After perhaps 10,000 to 100,000 years, the magnetic field weakens, and the magnetar settles into a more ordinary neutron star state. Their rarity may partly reflect this short, active lifetime. Only a few dozen confirmed magnetars exist in our galaxy and nearby galaxies. They are difficult to detect because their activity is sporadic. Most of the time they remain relatively quiet, emitting X-rays steadily. Then suddenly, without warning, they erupt in flares. Astronomers monitor the sky continuously to catch these transient bursts. Each detection provides clues about the interior physics of these extraordinary stars. Inside a magnetar, matter remains in the exotic state characteristic of neutron stars, superdense nuclear material, possibly including superfluid neutrons and superconducting protons. But the magnetic field adds another layer of complexity. It may penetrate deep into the core, influencing particle behavior at fundamental levels. The interplay between nuclear forces, gravity, and magnetism inside a magnetar remains an active area of research. The strength of the magnetic field also slows the magnetar's rotation more rapidly than in ordinary pulsars. As electromagnetic radiation carries away energy, the star's spin gradually decreases. Some magnetars rotate once every few seconds, relatively slow compared to millisecond pulsars. Their timing irregularities, sudden changes in rotation rate called glitches, provide additional insight into their internal structure. The phrase twisting atoms is not exaggeration. In magnetic fields above roughly 1012 Gauss, atomic orbitals elongate. In the magnetar regime, the distortion becomes extreme. The structure of matter adapts to the direction of the field, forming needle-like shapes. The physics governing such behavior arises from quantum theory, yet it plays out on a cosmic scale. A magnetar is thus a macroscopic embodiment of quantum electrodynamics under extraordinary conditions. Because magnetars are rare, violent, and mysterious, they often occupy the frontier of astrophysical research. Some fast radio bursts, brief, intense pulses of radio waves detected from distant galaxies, have been linked to magnetar activity. In 2020, a magnetar within the Milky Way produced a burst resembling extragalactic fast radio bursts, strengthening the case that at least some of these enigmatic signals originate from magnetars. Their violence, however, is episodic. Between flares, magnetars are quiet. They cool gradually, emitting X-rays as residual heat escapes. Their magnetic fields decay slowly. The surrounding space remains warped not only by gravity but by magnetism. Charged particles spiral along field lines, producing persistent radiation. If you could somehow observe a magnetar up close from a safe vantage point, you might see a small, dense star glowing faintly in X-rays. Occasionally, cracks would ripple across its crust, invisible to the eye but detectable through bursts of gamma radiation. the magnetic field would arc outward in immense loops, sculpting the behavior of particles in surrounding space. Magnetars also contribute to the chemical enrichment of the universe indirectly. Through supernova explosions and neutron star mergers, heavy elements are synthesized and dispersed into interstellar space. Though magnetars themselves are remnants, their progenitor stars and potential collisions play roles in cosmic recycling. There is a subtle philosophical resonance in their existence. The universe contains not only vast emptiness and gentle starlight, but also concentrated extremes, regions where familiar physics stretches to its limits. Magnetars remind us that the cosmos is not uniform in intensity. It contains calm regions like cosmic voids and violent bursts like giant flares. The strongest magnetic fields known, twisting atoms, rare, violent, mysterious. These are not mere descriptors but defining qualities. Magnetars sit at the intersection of gravity, nuclear physics, and magnetism, representing one of the most extreme stable configurations matter can assume short of collapsing into a black hole. As you imagine the night sky, remember that among the countless stars, a few compact remnants pulse quietly, their magnetic fields immense beyond comparison. Somewhere in the Milky Way, a magnetar may be building stress within its crust, preparing for another sudden flare. Its presence is mostly unnoticed from Earth, yet its physics challenges our understanding at fundamental levels. The universe does not confine itself to moderate conditions. It explores extremes, densities beyond comprehension, gravities that slow time, magnetic fields that reshape atoms. Magnetars are one such exploration. Brief in their active lives, fierce in their eruptions, they illuminate corners of physics unreachable in laboratories. And in the vast calm between galaxies and filaments, in the deep quiet of space, these compact stars carry within them fields strong enough to bend light, twist matter, and unleash bursts felt across interstellar distances. Rare, powerful, and enigmatic, magnetars are among the most intense expressions of cosmic possibility. There is something deeply comforting about the steady ticking of time. Seconds follow seconds. Minutes stack into hours. Days become years. We experience time as a constant current flowing forward at the same pace for everyone, everywhere. It feels fixed, reliable, universal. And yet the universe tells a very different story. Time is not absolute. It is not the same everywhere. It stretches, compresses, bends, and slows depending on motion and gravity. Time itself is part of the fabric of reality, woven together with space in a single structure called space-time. And under certain conditions, that fabric does not remain smooth. To understand time dilation, we begin with gravity. According to general relativity, gravity is not a force pulling objects together in the traditional sense. Instead, mass curves space-time, and objects follow the curved paths laid out by that geometry. The more massive an object, the more it bends space-time around it. This curvature affects not only how objects move, but how time passes. Imagine two identical clocks. One rests far from any massive body, floating quietly in deep interstellar space. The other sits on the surface of a dense object, perhaps a neutron star or near the edge of a black hole. The clock closer to the massive object will tick more slowly compared to the one far away. This is gravitational time dilation. The stronger the gravity, the slower time flows relative to distant observers. This is not a metaphor. It has been measured directly. Atomic clocks placed at different altitudes on Earth tick at slightly different rates. A clock on a mountain runs faster than a clock at sea level because it is slightly farther from Earth's center of mass. The difference is tiny, fractions of a second over many years, but it is measurable. Satellites orbiting Earth must account for both gravitational time dilation and velocity-based time dilation to keep navigation systems accurate. Without correcting for these relativistic effects, GPS would drift by kilometers within a day. The idea that time slows near gravity feels counterintuitive because we are accustomed to thinking of time as separate from space. But in relativity, space and time are inseparable. Massive objects curve not only spatial dimensions but the temporal dimension as well. Near a black hole, this effect becomes dramatic. To a distant observer, a clock approaching the event horizon appears to slow almost to a halt. Signals sent outward stretch into longer and longer wavelengths, fading and reddening. From afar it would seem as though the clock never quite crosses the horizon, frozen in time. Yet for the clock itself, time continues normally. If someone were falling toward a black hole, they would not experience their own clock slowing. Their heartbeat would feel steady. Their thoughts would proceed as usual. The slowing occurs relative to someone watching from a safe distance. Time dilation is relational. It depends on the observer's frame of reference. Gravity is only part of the story. Motion also affects time. According to special relativity, when an object moves at high speed relative to an observer, time on that moving object slows down compared to the observer's frame. This effect becomes significant as speeds approach the speed of light. The faster you travel, the slower your clock ticks relative to someone at rest. This phenomenon has been tested repeatedly. Particles accelerated to near light speed in laboratory experiments decay more slowly than identical particles at rest. Their internal clocks run slower because of their motion. Even commercial airline flights experience measurable time dilation. Atomic clocks flown around the world return showing slight differences compared to stationary clocks on the ground. The combination of motion and gravity leads to fascinating consequences for astronauts. An astronaut aboard the International Space Station moves at roughly 28,000 kilometers per hour. Due to velocity-based time dilation, their clock runs slightly slower than clocks on Earth. However, because the station orbits above Earth's surface where gravity is weaker, gravitational time dilation causes their clock to run slightly faster than clocks at sea level. The net result is a small difference. Astronauts age by tiny fractions of a second differently than people on Earth. Over a 6-month mission, the difference amounts to microseconds. It is small, but real. If humans could travel at speeds close to light, the effect would become profound. Imagine a spacecraft capable of reaching 99.9% of the speed of light. For the travelers aboard, time would pass more slowly compared to Earth. They might journey for a few years according to their own clocks, while decades or centuries pass on Earth. Upon returning, they would find that far more time had elapsed for those who remained behind. This is often called the twin paradox, though it is not truly a paradox but a consequence of relativity's geometry. Time is not fixed. It is not a universal river flowing at identical rates for all observers. It is elastic, shaped by motion and gravity. The faster you move, the slower your time relative to others. The deeper you sit in a gravitational well, the slower your time relative to those farther out. These are not distortions of perception, but fundamental aspects of space-time structure. Consider again the vicinity of a black hole. Near its event horizon, gravitational time dilation becomes extreme. A distant observer watching an infalling astronaut would see their movements slow, their voice deepen in pitch as signals stretch until they fade into darkness. Yet the astronaut would cross the horizon in finite time according to their own clock. Two perspectives, equally valid within their frames, describing different experiences of time. Neutron stars also exhibit measurable time dilation. Their intense gravity slows clocks at their surface relative to distant observers. Light emitted from a neutron star is redshifted as it climbs out of the gravitational well. This redshift provides evidence for the star's compactness and the strength of its gravity. Even on Earth, though we do not feel it directly, time dilation operates continuously. Every time you climb a staircase, your clock changes rate ever so slightly compared to someone below. The effect is minuscule, but the principle holds universally. Time is not uniform. It responds to the distribution of mass and motion. The deeper philosophical implication is subtle yet profound. If time flows differently depending on location and velocity, then there is no single universal present moment shared by all observers. Events that appear simultaneous in one frame may not be simultaneous in another. The structure of reality includes multiple valid slices of now, depending on perspective. This does not mean time is an illusion. It means time is part of geometry. Just as distance depends on the path taken through space, elapsed time depends on the path taken through space-time. In relativity, the longest path through time between two events is experienced by an observer who remains at rest in a weak gravitational field. Accelerated motion or stronger gravity shortens the experienced duration. The concept of space-time helps unify these ideas. Instead of picturing time as separate from space, imagine a four-dimensional fabric where events have both spatial coordinates and a temporal coordinate. Massive objects curve this fabric. Moving objects trace paths through it. The rate at which time passes corresponds to the geometry of those paths. Gravitational waves, ripples in space-time caused by massive accelerating objects like merging black holes, briefly stretch and compress space-time itself. In principle, they momentarily alter distances and durations as they pass. Though the effect on everyday clocks is extraordinarily tiny, it reinforces the idea that space-time is dynamic. Astronauts age differently, though only slightly under current technological limits. But the principle opens imaginative possibilities. In a far future where interstellar travel approaches relativistic speeds, travelers could leap into distant epochs relative to Earth's timeline. Time dilation becomes a bridge between eras. Yet even without dramatic voyages, we live in a universe where time is fluid. GPS satellites correct for relativistic effects every second to maintain accuracy. Experiments confirm predictions with astonishing precision. The bending of light near massive objects, the redshift of signals climbing out of gravity wells, the extended lifetimes of fast-moving particles, all align with the idea that time is not fixed. There is a quiet elegance in this. Time responds to structure. It slows in valleys of gravity. It stretches under speed. It weaves together with space into a flexible continuum. The ticking of a clock depends on where it sits and how it moves. As you rest and imagine the cosmos, consider two observers separated by vast distances, one orbiting near a massive star, another drifting in deep space. Their clocks disagree slightly. Neither is wrong. Each measures time faithfully within their frame. The universe accommodates both perspectives. Time slows near gravity. Astronauts age differently. Time is not fixed. These are not poetic statements, but measurable truths. They remind us that reality is richer than intuition suggests. The flow of moments is shaped by the structure of space-time itself. And as the universe expands, as galaxies drift and black holes bend geometry inward, time continues to unfold, elastic, relational, woven into the curvature of existence. There is something about time that feels directional. You remember yesterday, but not tomorrow. A glass can fall from a table and shatter on the floor, but the shards do not spontaneously leap upward and reassemble into a perfect form. Ice melts into water. Water does not ordinarily gather itself back into solid cubes without a freezer humming nearby. The universe seems to favor one direction. Events unfold from past to future. Causes precede effects. We call this asymmetry the arrow of time. And yet, when we examine the fundamental laws of physics, something curious emerges. Many of the equations that govern motion, electromagnetism, and even quantum interactions work equally well forward and backward. If you filmed two billiard balls colliding and reversed the footage, the motion would still obey Newton's laws. On microscopic scales, physics does not strongly prefer a direction. So why does the macroscopic world, the world of melting ice and aging stars, clearly move forward? The answer lies in entropy. Entropy is often described as a measure of disorder, though that word can be misleading. More precisely, entropy measures the number of microscopic arrangements corresponding to a macroscopic state. A tidy deck of cards arranged in perfect numerical order represents a highly specific configuration. There are very few ways to achieve that exact order. Shuffle the deck, however, and you create one of many possible disordered arrangements. There are vastly more disordered combinations than ordered ones. Entropy quantifies this difference. The second law of thermodynamics states that in an isolated system, entropy tends to increase. It does not say entropy always increases without exception, but that statistically systems move toward states with more possible configurations. A broken glass on the floor corresponds to many more microscopic arrangements than an intact glass standing upright. the shattered state is overwhelmingly more probable. This statistical tendency gives rise to the arrow of time. Imagine again the glass falling from the table. The atoms within the glass and the floor follow the laws of physics exactly. Nothing in those laws forbids the fragments from reassembling. But the probability of all those atoms spontaneously moving into precisely the right configuration is astronomically small. The forward direction, from order to disorder, is vastly more likely than the reverse. Entropy increases and time appears to move forward. The early universe provides a profound clue to why this arrow exists. Observations of the cosmic microwave background reveal that the universe began in a state of extraordinary uniformity. Matter and radiation were distributed almost perfectly evenly, with only tiny fluctuations. In terms of gravity, this uniform state represents low entropy. Although uniformity might seem disordered, gravitational systems behave differently from ordinary gases. In gravity-dominated systems, clumping increases entropy. The formation of stars, galaxies, and black holes represents a rise in gravitational entropy. Thus, the universe began in a special low entropy condition. From that beginning, entropy has been increasing ever since. Stars form and burn fuel, converting nuclear energy into radiation that spreads outward. Structures assemble and eventually decay. Black holes merge, growing more massive and increasing overall entropy dramatically. The arrow of time is tied to this cosmic journey from low entropy to higher entropy. Why did the universe begin in such a low entropy state? That remains one of the deepest open questions in cosmology. The laws of physics permit many possible initial configurations, yet ours appears remarkably ordered in its early moments. The existence of the arrow of time depends on that initial condition. Without a low entropy beginning, there would be no thermodynamic gradient for time to follow. Entropy also explains why we remember the past but not the future. Memory formation involves physical processes in the brain that increase entropy overall. To record a memory, energy must be expended and heat dissipated. This aligns memory with the direction of increasing entropy. You cannot remember the future because entropy does not decrease spontaneously to encode events that have not yet occurred in your frame. On a cosmic scale, entropy continues to rise. Stars convert hydrogen into heavier elements, radiating energy into space. Eventually, star formation will decline as available gas becomes locked in stellar remnants or expelled. Over trillions of years, galaxies will grow dim. Black holes will dominate, slowly evaporating through Hawking radiation across unimaginable timescales. The universe may approach a state of maximum entropy, a condition sometimes called heat death, where usable energy is exhausted and change becomes minimal. But does entropies increase absolutely forbid time from reversing? The fundamental laws do not prohibit microscopic reversibility. In principle, if every particle in the universe were reversed precisely in velocity and position, processes would run backward. Broken glasses would reassemble. Smoke would gather into flames. Memories would unwind. Yet achieving such a reversal would require an impossibly precise arrangement of conditions. The statistical improbability is so extreme that it effectively never occurs. There are subtleties, however. Certain interactions in particle physics exhibit slight asymmetries between matter and antimatter, known as CP violation. These effects introduce tiny differences between forward and backward processes at fundamental levels, but they are not responsible for the everyday arrow of time. That arrow arises overwhelmingly from entropy. The expansion of the universe also contributes to the story. As space stretches, it provides room for entropy to increase. Radiation cools, structures form, and gravitational clumping continues. The cosmic arrow and the thermodynamic arrow appear aligned. Both point from a dense, uniform past toward a structured, evolving future. Philosophically, the arrow of time shapes experience itself. Consciousness unfolds sequentially. Causes lead to consequences. Stories have beginnings and endings. If entropy did not increase, our perception of time might be profoundly different or non-existent in its current form. The very concept of before and after depends on irreversible processes. Imagine a universe at maximum entropy. No temperature differences remain. No energy gradients drive change. In such a state, processes would occur at equilibrium. Without gradients, there would be no engines, no metabolism, no stars. Time might still exist geometrically, but it would lose its experiential arrow. Nothing would happen in a meaningful sense. Could there be regions where entropy decreases locally? Yes, but only by increasing entropy elsewhere. Living organisms, for example, maintain internal order by exporting entropy to their environment. The overall entropy of the universe continues rising even as pockets of complexity form. This interplay between local order and global disorder allows galaxies, planets, and life itself to exist. Speculations about time reversal often arise in cosmology. Some theories propose that the arrow of time might reverse in a contracting universe. Others imagine a symmetric cosmos where time flows outward in two directions from a low-entropy midpoint. These ideas remain speculative and unconfirmed. Observations suggest our universe is expanding and accelerating, not contracting. At a practical level, the arrow of time defines causality. You cannot send a message to yesterday because doing so would require entropy to decrease. Information transmission depends on irreversible processes. The asymmetry ensures that causes precede effects in every observed scenario. And yet, the laws at the smallest scales remain almost indifferent to direction. This tension between microscopic reversibility and macroscopic irreversibility gives rise to ongoing debates in physics and philosophy. Some argue that the arrow is emergent, not fundamental. It arises from boundary conditions rather than intrinsic laws. Consider once more the shattered glass. Each fragment's motion obeys time-symmetric equations, but the overwhelming number of ways for fragments to scatter compared to reassemble ensures the forward direction dominates. Entropy is not a force but a statistical tendency. It governs the large-scale flow of events. As you lie quietly, perhaps thinking of moments that have passed, or imagining moments yet to come, remember that this flow is not merely psychological. It is written into the thermodynamic history of the universe. From the smooth early cosmos to today's intricate structures, entropy has been rising steadily. Why does time move forward? Because the universe began in a special low-entropy state, and statistical laws favor increasing disorder. Entropy and disorder shape the arrow. Could it reverse? In principle, under fantastically improbable conditions, but in practice, the forward direction dominates overwhelmingly. Time's arrow is not an illusion, nor is it a fundamental force. It is a consequence of probability, of initial conditions, of the universe's unfolding structure. It guides stars toward burnout, civilizations toward memory, and glasses toward shattering rather than reforming. And as the cosmos continues expanding, as entropy climbs gradually higher, the arrow remains steady, pointing from past to future, from lower entropy to higher, from beginnings toward endings yet unwritten. There is a quiet moment, usually late at night, when the world feels almost too precise. The laws of physics hum along with mathematical elegance. Constants hold steady across billions of light years. Electrons carry exactly the same charge everywhere we look. The speed of light never wavers. Gravity obeys equations that can be written on a page. It is in these moments that a subtle question sometimes arises. What if reality itself is not fundamental? What if what we experience as the physical universe is, in some deeper sense, computed? The simulation hypothesis suggests that our universe might be the product of an advanced form of information processing. Not a metaphorical simulation, but a literal one. A reality generated by an underlying computational structure. In this view, space, time, matter, and energy could be emergent properties of something more basic, much as images and environments emerge from code within a digital system. This idea does not originate from fantasy alone. It arises from the increasing recognition that the universe behaves mathematically. Physical laws can be expressed in compact symbolic form. Constants appear fixed and finely tuned. Quantum mechanics describes particles as probability amplitudes governed by equations. General relativity expresses gravity as geometry. At the deepest levels we can currently probe, reality resembles information structured through rules. Is reality computed? That question rests on whether the universe is fundamentally continuous or discrete. If space and time can be divided indefinitely into smaller units, then the analogy to digital computation weakens. But some theories of quantum gravity suggest that space-time may have a smallest scale, the Planck length and Planck time, below which the concept of distance or duration loses meaning. If there is a smallest unit, then reality might resemble pixels in space and frames in time. Quantum mechanics also introduces a curious feature, indeterminacy. Particles do not possess definite properties until measured. Their states exist as probabilities. When observation occurs, one outcome becomes real. This has led some thinkers to draw parallels with computational rendering, where only parts of a virtual environment are fully calculated when needed. While such comparisons remain speculative, they capture the imagination. Physical constants too have been compared to parameters in code. The strength of gravity, the charge of the electron, the mass of fundamental particles. These values appear finely balanced to allow complex structures to form. Slight changes in certain constants could prevent stars from igniting or chemistry from stabilizing. In a simulated universe, constants might be set deliberately, much like parameters in a program. Yet caution is essential. The fact that something can be described mathematically does not imply it is computed in a literal sense. Mathematics is the language of structure. The universe may obey mathematical laws because mathematics describes consistent patterns, not because it runs on code. Still, the idea persists. If a civilization advanced far enough technologically, might it create simulations detailed enough to contain conscious beings? Modern computing already generates immersive virtual environments. Though primitive compared to reality, they hint at the possibility of more advanced systems. If such civilizations are common in the cosmos and capable of running many simulations, then statistically simulated realities might vastly outnumber base realities. In that scenario, any randomly selected conscious observer would more likely inhabit a simulation than the original physical universe. This line of reasoning is philosophical rather than empirical. It does not rest on experimental evidence but on probabilistic arguments about future technology and the nature of consciousness. And it leads to deeper questions. What would it mean for reality to be computed? Would there be a base universe beyond ours? Could the simulation be nested within others, layers upon layers of generated realities? Some physicists have speculated about detectable signs of computational limits. Perhaps space-time might show a lattice-like structure at very small scales. Perhaps there could be maximum information density limits corresponding to processing capacity. Perhaps certain physical anomalies might hint at underlying discretization. Yet so far, no conclusive evidence points toward an artificial substrate. Even if reality were computed, the laws we observe would remain consistent within our frame. From inside the simulation, physics would appear seamless. Just as characters in a sophisticated digital world experience their environment as continuous, inhabitants would perceive their physical laws as fundamental. The hypothesis also intersects with ancient philosophical themes. For centuries, thinkers have questioned whether sensory experience corresponds directly to ultimate reality. Plato imagined shadows on a cave wall mistaken for truth. Later, philosophers wondered whether the world could be a dream. The simulation hypothesis is a modern extension of this lineage, reframed in computational terms. If reality is computed, then space and time might be emergent, not primary. The underlying substrate could operate in ways we cannot perceive. Our entire cosmos, with its galaxies, black holes, and cosmic background radiation, could be data processed at unimaginable scales. Yet from within it would feel entirely real. There is a calming aspect to this reflection. Whether simulated or fundamental, the universe still follows consistent rules. Stars shine, gravity pulls, entropy increases. Meaning and experience arise within the system, regardless of its ultimate origin. If consciousness emerges from information patterns, then those patterns are meaningful within their context. One might ask whether a simulated universe diminishes significance. If everything is code, does anything matter? But consider this. A story told within a novel remains meaningful to its characters, even if they exist only as ink on paper. Experiences within a simulated environment would still be genuine experiences for those inside it. Pain would feel real. Joy would feel real. curiosity would feel real. Another angle involves information theory. Some physicists suggest that information, not matter, is the most fundamental aspect of reality. In this perspective, particles are excitations of fields, and fields encode information. Black hole thermodynamics hints that information content relates to surface area rather than volume. The holographic principle proposes that the information describing a region of space might be encoded on its boundary. These ideas do not confirm simulation, but they suggest that information lies at the core of physical law. If physical constants resemble code, they could also reflect deeper necessity. Perhaps there is only one consistent set of laws that allows stable complexity. Or perhaps countless variations exist in a multiverse, and we inhabit one that permits observers. The simulation hypothesis is one possibility among many attempting to explain fine-tuning. A philosophical calm reflection might ask whether the distinction between simulated and real is meaningful at all. If our experiences arise from consistent interactions governed by stable rules, then they constitute reality within our frame. Whether those rules are computed by another layer of physics does not alter the lived structure of existence. Suppose for a moment that reality is computed. The stars would still burn in accordance with equations. Time dilation would still slow clocks near gravity. Entropy would still define the arrow of time. The fact of computation would not negate physical law. It would simply relocate its foundation. And suppose reality is not computed. Suppose it is fundamental and irreducible. The mathematical elegance of physics would then reflect intrinsic structure rather than programming. Either way, the universe remains remarkable. The simulation hypothesis also invites humility. It reminds us that our current understanding may not reach ultimate layers. Just as characters in a game cannot access the hardware running their world, we may be unable to access whatever substrate underlies ours, if such a substrate exists. Yet speculation should not replace empirical inquiry. Science advances through observation and testable prediction. So far, the simulation hypothesis offers intriguing possibilities, but no direct experimental confirmation. It occupies the borderland between physics and philosophy. Still, there is something soothing about contemplating it. The idea that reality might be information arranged by deeper rules does not necessarily unsettle. It can evoke a sense of layered depth, of nested structures extending beyond perception. As you rest and let your thoughts drift, imagine the universe as a vast tapestry of information, woven through space and time. Galaxies become patterns in data. Particles become bits of state evolving according to rules. Consciousness becomes a dynamic arrangement of information aware of itself. Whether computed or fundamental, the cosmos unfolds with coherence. Physical constants remain steady. Laws operate consistently. The night sky remains luminous with stars whose light has traveled billions of years. Is reality computed? Perhaps. Physical constants like code? Possibly. But regardless of ultimate substrate, the experiences within this universe are real to those who inhabit it. The calm reflection lies in recognizing that even if there is another layer beneath ours, this layer remains meaningful. The universe, simulated or not, continues expanding. Stars ignite and fade. Entropy rises, minds ponder existence. And somewhere within this immense structure, whether coded or fundamental, awareness looks outward and wonders. And that wondering itself, the quiet act of reflection, remains one of the most remarkable phenomena of all. There was a time when the word universe meant everything, all space, all time, all matter, a single self-contained totality. But as cosmology deepened and theoretical physics pushed beyond the visible horizon, that certainty began to soften. What if our universe is not the only one? What if what we call the cosmos is just one region within something far larger? A vast expanse containing many realities, each with its own properties, histories, and perhaps even its own physical laws. This is the idea of the multiverse. The multiverse is not one single theory, but a family of ideas emerging from modern physics. It does not begin with imagination alone. It grows from attempts to explain puzzling features of our observable universe. One of the most influential paths to the multiverse begins with cosmic inflation. Inflation proposes that in the earliest fraction of a second after the Big Bang, the universe underwent an extraordinary burst of exponential expansion. Space itself expanded faster than the speed of light. Not objects moving through space, but space stretching. This rapid growth explains several otherwise mysterious features of the cosmos. It accounts for why the universe appears remarkably flat on large scales. It explains why regions far apart in the sky have nearly identical temperatures, even though they seem too distant to have ever communicated. Inflation smooths and stretches space-time, ironing out irregularities. But inflation may not have happened just once in a clean, single event. In many models, inflation is driven by a quantum field, a scalar field permeating space. Quantum fields are subject to fluctuations. In some regions, inflation may have ended quickly, allowing ordinary expansion and galaxy formation to begin. In other regions, inflation might have continued longer, and in still others, it might still be ongoing. This leads to the concept of eternal inflation. In this picture, inflation does not stop everywhere simultaneously. Instead, it ends locally in pockets, forming what we perceive as individual universes. Each pocket becomes a bubble universe, expanding and cooling to form matter, stars, and galaxies. Meanwhile, outside these bubbles, inflation continues, stretching space further and spawning new bubbles endlessly. If this scenario is correct, then our universe is one bubble among potentially countless others. Each bubble might have slightly different physical conditions depending on how the inflationary field settled in that region. The constants of nature, such as particle masses or force strengths, could vary from bubble to bubble. This possibility connects to another area of theoretical physics, string theory. In some formulations of string theory, there exist an enormous number of possible vacuum states, different stable configurations of extra dimensions and fields. Each configuration corresponds to a distinct set of physical laws and constants. If inflation populates these possible states randomly across different bubbles, then the multiverse becomes a vast landscape of varied realities. In such a landscape, some universes might resemble ours closely, others might differ in subtle ways, and some might be radically different. Universes where gravity is stronger, where chemistry cannot stabilize, where stars never form, or where matter behaves in unfamiliar patterns. Most such universes might be sterile, lacking the complexity required for observers. But in a sufficiently large multiverse, even rare configurations become inevitable somewhere. This reasoning is sometimes invoked to address the fine-tuning problem. The physical constants in our universe appear delicately balanced to allow complex structures. If gravity were slightly stronger, stars might burn too quickly. If the cosmological constant were much larger, galaxies might never form. One explanation is that only certain values permit observers to exist. In a multiverse with varied constants, we naturally find ourselves in one of the rare universes where conditions allow complexity. This is known as anthropic reasoning. The multiverse, then, is not necessarily a claim that everything imaginable exists. It is a consequence of certain physical models extended logically. If inflation behaves in specific ways, and if high-energy physics allows multiple stable vacuum states, then many realities may arise inevitably. Yet the multiverse poses a profound challenge. It may be impossible to test directly. Other bubble universes, if they exist, would lie beyond our observable horizon. Space between bubbles continues inflating, separating them faster than light can traverse. No signal from another universe could reach us if inflation keeps stretching the space between. There have been speculative ideas about indirect evidence. If two bubble universes collided in the early stages, perhaps subtle imprints might appear in the cosmic microwave background, circular anomalies or temperature distortions. Astronomers have searched for such signatures, but none have been conclusively identified. So far, the observable data align with a single universe model just as well as with many multiverse scenarios. This raises a philosophical tension. Science traditionally relies on falsifiability, the ability to test and potentially disprove a theory. If the multiverse cannot be tested, does it remain scientific? Some argue that it is a legitimate prediction of inflationary models already supported by evidence. If inflation is confirmed more strongly, And if its mathematics naturally yields eternal inflation, then the multiverse follows as a consequence. Others caution that without empirical access, it risks becoming metaphysics. Still, the multiverse remains plausible within current frameworks. It is not arbitrary fantasy. It emerges from equations that attempt to describe the earliest moments of cosmic history. Whether those equations reflect reality fully is an open question. There are also other forms of multiverse proposals. In quantum mechanics, the many worlds interpretation suggests that every quantum event with multiple possible outcomes results in branching realities. Each outcome becomes real in its own branch. In this view, the universe constantly splits into parallel histories, each containing different results of microscopic events. Unlike inflationary bubbles, these branches coexist within a shared quantum structure. There are also mathematical multiverse proposals suggesting that all mathematically consistent structures exist physically somewhere, and cyclic models of cosmology propose sequences of expansions and contractions, perhaps generating new universes over time. These ideas vary widely, but they share a common thread. Reality may be larger than the observable cosmos. Our universe might not be the totality, but a region within a broader ensemble. What would it mean if that were true? From within our bubble, physics remains consistent. Stars burn according to our constants. Gravity behaves predictably. The existence of other universes would not alter daily experience. It would expand perspective rather than disrupt law. The notion that many realities exist can feel unsettling at first. It challenges the uniqueness of our cosmos, yet it also invites a sense of vastness beyond imagination. If countless universes exist, each with its own history, then possibility stretches beyond the limits of our own cosmic timeline. There is calm in recognizing that even if the multiverse is real, it does not diminish the value of our universe. Our region of space-time, with its galaxies and life-bearing planets, remains meaningful within its own structure. Whether alone or one among many, it is the environment in which consciousness has emerged. The impossibility of direct testing may frustrate scientific certainty, but it also reflects humility. There may be boundaries to observation set by cosmic expansion itself. Horizons define what can be seen. Beyond them, speculation remains guided by theory rather than measurement. Inflation and bubble universes, many realities, impossible to test, yet plausible. The multiverse rests at the edge of knowledge, where mathematics suggests grand possibilities and observation remains silent. As you let your thoughts drift across cosmic scales, imagine our universe as one luminous bubble floating within an ever-expanding sea of inflation. Around it, countless other bubbles may shimmer into existence, each with its own space-time unfolding. We cannot travel between them, we cannot see them, yet their possibility emerges from the same equations that describe our own beginning. Whether the multiverse exists or not, the act of contemplating it expands the imagination. It reminds us that the observable horizon may not mark the boundary of reality. It encourages curiosity without certainty, and perhaps that is enough. To rest in the awareness that the cosmos might be broader than we can measure, richer than we can confirm, layered beyond perception. Many realities may exist, or perhaps only this one does. Either way, our universe continues expanding, galaxies drifting under dark energy's quiet influence, stars burning steadily. Within this bubble, or this singular cosmos, time flows, entropy rises, and minds ponder the vastness. The multiverse remains a possibility suspended at the frontier of physics, impossible to test directly, yet born from plausible mathematical insight. And in that open space between knowledge and mystery, the imagination finds room to wander gently, without urgency, across possibilities as wide as existence itself. On clear nights, when the sky is dark enough and the air is still, the Milky Way stretches overhead like a quiet river of light. Each faint point is a star. Many of those stars have planets. Some of those planets orbit in regions where liquid water could exist. In the last few decades, astronomers have confirmed what was once speculation. Planets are common. Our galaxy alone likely contains hundreds of billions of stars, and statistical surveys suggest that a significant fraction host planetary systems. Among those, Billions may reside in habitable zones, regions neither too hot nor too cold, where conditions might allow life as we understand it, and yet the sky remains silent. This tension between expectation and observation is known as the Fermi paradox. The name comes from physicist Enrico Fermi, who reportedly asked during a casual lunchtime conversation in 1950, "Where is everybody?" It was not a whimsical remark, but a pointed question. Given the age of the galaxy, over 13 billion years, and the vast number of potentially habitable worlds, even modest assumptions about life and intelligence suggest that technological civilizations should have arisen many times. If even a small fraction developed interstellar travel or long-lasting communication technologies, signs of their presence might be detectable. But so far we have found none. Billions of habitable planets, the silence of the sky. Are we early or alone? To understand the paradox, it helps to consider scale and time. The Milky Way is about 100,000 light-years across. Even traveling at a small fraction of light speed, a civilization could in principle spread across the galaxy within a few million years, a blink compared to cosmic timescales. If intelligent life commonly develops and expands, the galaxy might already be saturated with its traces. Yet our radio telescopes detect no clear signals. Our surveys find no alien megastructures. The sky shows only natural astrophysical processes. One response to the paradox is to question the assumptions. Perhaps life itself is rare. While simple microbial life might emerge under suitable conditions, the transition from simple to complex multicellular organisms could be extraordinarily unlikely. On Earth, life appeared relatively early in our planet's history, but complex organisms took billions of years to evolve. Intelligence capable of technology emerged only recently. Perhaps most habitable planets remain dominated by simple life forms. Another possibility concerns the Great Filter, a term used to describe a hypothetical barrier in the progression from simple matter to advanced civilizations. The filter could lie behind us. Perhaps the origin of life or the development of complex cells is exceedingly rare. If so, we may be fortunate survivors of a highly improbable chain of events. Alternatively, the filter could lie ahead. Perhaps technological civilizations tend to self-destruct before achieving interstellar presence. Nuclear war, environmental collapse, runaway artificial intelligence, or other unforeseen challenges could curtail longevity. The Great Filter hypothesis carries both reassurance and unease. If the filter is behind us, our existence is extraordinarily rare, but perhaps stable. If it lies ahead, the silence may serve as a warning. There are also more mundane explanations. Interstellar travel may be far more difficult than imagined. Even at advanced technological levels, the energy requirements and timescales involved are immense. Civilizations might remain confined to their home systems, communicating only locally. Or they may lose interest in outward expansion, turning inward toward digital or virtual realities. Communication methods may differ from our expectations. We have searched primarily for radio signals because radio waves travel efficiently across interstellar distances and because our own civilization used radio heavily in its early technological phase. But advanced societies might shift to communication technologies that are less detectable or more efficient in ways we do not yet understand. It is also possible that we have not been listening long enough. Radio astronomy capable of detecting faint extraterrestrial signals has existed for only about a century. That is a fleeting moment compared to the age of the galaxy. Civilizations could rise and fall over timescales that do not overlap with our brief window of listening. Another perspective suggests that the galaxy may not be as hospitable as raw numbers imply. Many stars differ significantly from our sun. Red dwarfs, which are common, often produce intense stellar flares that could strip atmospheres from nearby planets. Habitable zones around such stars lie close enough that tidal locking might affect climate stability. Giant planets migrating inward could destabilize terrestrial orbits. The formation of stable, life-supporting environments may require a delicate balance of conditions. Then there is the possibility that intelligent life exists, but chooses silence. Perhaps advanced civilizations adopt a policy of non-interference, avoiding contact with emerging species. Or perhaps broadcasting signals openly carries risks. In a galaxy with unknown inhabitants, caution might prevail. Some have speculated about hidden signs, Large-scale engineering projects, such as hypothetical Dyson spheres, structures built to capture a star's energy output, could produce distinctive infrared signatures. Astronomers have searched for unusual infrared excesses in stellar surveys, but have found no confirmed artificial constructs. The absence of evidence does not prove absence, but it narrows the range of possibilities. The Fermi paradox remains powerful because it combines optimism with emptiness. The cosmos seems fertile with potential, yet observation yields quiet. Are we early? Perhaps the universe has only recently become suitable for long-lived technological life. Heavy elements necessary for complex chemistry were forged gradually through stellar generations. Early galaxies lacked sufficient metallicity for rocky planets. Maybe only in the last few billion years have conditions stabilized enough for complex ecosystems to develop. If so, we may be among the first wave of technological species. This idea carries a different kind of significance. If we are early, then the future of life in the galaxy may depend on choices made by civilizations like ours. The silence would not signal absence, but youth. Or are we alone? The possibility is stark yet not impossible. Perhaps the chain of events leading to conscious observers capable of radio telescopes is so improbable that it has occurred only once in our galaxy, or even once in the observable universe. If that were true, the responsibility resting on our species would be immense. The universe would contain vast expanses of beauty and complexity, yet no other minds to contemplate them. However, caution tempers such conclusions. Our observational tools remain limited. We have surveyed only a fraction of the sky in detail. Our instruments detect only certain types of signals. The absence of confirmed extraterrestrial intelligence reflects current capability, not definitive proof. The paradox also invites reflection on timescales. The galaxy's age exceeds 13 billion years. Human civilization has existed for only a few thousand years in technological form. Even our modern electronic era spans less than a century. It may be unrealistic to expect immediate contact. Imagine an ancient forest stretching across a continent. Within it, a single firefly begins to glow briefly in one clearing. It looks around and sees no other lights, concluding perhaps that it is alone. Yet the forest is vast, and other fireflies may glow at different times or in distant groves beyond sight. The silence does not necessarily imply emptiness. The Fermi paradox does not demand a single answer. It invites layered possibilities. Life may be rare, intelligence may be rarer, longevity may be fragile, communication methods may differ. We may be early, we may be isolated by distance and time, or perhaps we simply have not recognized the signals yet. There is also a subtle anthropic consideration. Observers arise only in universes and environments where conditions allow their existence. The fact that we find ourselves in a seemingly quiet galaxy may not be surprising if complex life is intrinsically uncommon. The search continues. Radio telescopes scan the skies. Optical surveys analyze stellar spectra. Space missions search for biosignatures, atmospheric gases that might indicate life on exoplanets. The coming decades may reveal whether microbial life exists elsewhere, even if intelligent civilizations remain elusive. As you imagine the night sky, billions of habitable planets orbiting distant stars, consider both possibilities with calm curiosity. The silence may be temporary. It may reflect youth, distance, rarity, or caution. It may conceal subtle signals beyond our current detection. Are we early or alone? The question lingers without urgency. The cosmos remains vast, and our understanding continues evolving. If we are early, then the galaxy's future may be filled with emerging minds, each gazing outward as we do now. If we are alone, then the quiet beauty of stars and nebulae becomes even more profound, for consciousness has arisen at least once to witness it. Either way, the silence of the sky does not diminish wonder. It deepens it. It reminds us that exploration is ongoing, that knowledge grows gradually, that humility accompanies inquiry. Billions of habitable planets, the quiet expanse above, a species listening carefully for signals in the dark, and somewhere within that silence lies not necessarily emptiness, but possibility, waiting patient across the vast reaches of space and time. Look up at the night sky and you see constancy, points of light that seem fixed and eternal. Constellations that guided sailors centuries ago still trace the same patterns. The stars feel permanent, as though they will always be there, quietly burning against the dark. But stars are not eternal. They are engines running on finite fuel, and the future of stars is a story not of sudden endings, but of gradual transformation, a slow dimming across unimaginable spans of time. Every star shines because of fusion. In its core, immense pressure and temperature force hydrogen atoms together, fusing them into helium. This process releases energy according to Einstein's famous equation, converting tiny amounts of mass into radiant light and heat. That energy pushes outward against gravity's inward pull, creating a balance that can last billions of years. But hydrogen is not infinite. A star's life is a long negotiation between gravity and fuel, and eventually the terms change. For stars like our Sun, the main sequence phase, steady hydrogen burning, lasts about 10 billion years. We are roughly halfway through that span. The Sun shines now with quiet stability, but over time it will gradually grow brighter as fusion in the core alters its internal structure. In about 5 billion years, hydrogen in the core will be exhausted. Without outward pressure from fusion at its center, gravity will compress the core further, heating surrounding layers and igniting hydrogen in a shell. The outer layers will expand dramatically. The Sun will become a red giant, swelling far beyond its current size, perhaps engulfing the inner planets. This phase will not be abrupt. It will unfold slowly, over hundreds of millions of years. The sky, if anyone were watching from Earth, would brighten and redden. Oceans would evaporate. The surface would become uninhabitable long before the Sun reaches its maximum expansion. Eventually, the outer layers will drift away into space, forming a planetary nebula, a glowing shell of gas illuminated by the exposed core. What remains will be a white dwarf, a dense, Earth-sized remnant no longer producing energy through fusion, slowly cooling over trillions of years. But not all stars are like the Sun. The universe contains a range of stellar masses, and mass determines destiny. Massive stars burn hotter and brighter, but also far more quickly. A star 10 times the mass of the Sun may exhaust its fuel in tens of millions of years, a brief lifespan in cosmic terms. Such stars end in supernova explosions, dispersing heavy elements into space and leaving behind neutron stars or black holes. These violent endings enrich the interstellar medium, seeding future generations of stars and planets with carbon, oxygen, and iron. The most common stars, however, are not massive. They are red dwarfs, small, cool stars with masses far below that of the Sun. Red dwarfs burn their hydrogen slowly and efficiently. Unlike larger stars, they are fully convective, meaning hydrogen from throughout the star can circulate into the core and participate in fusion. This efficiency allows red dwarfs to last far longer than Sun-like stars. How long? Trillions of years. No red dwarf has yet reached the end of its life because the universe itself is only about 13.8 billion years old. Even the earliest red dwarfs formed have barely begun their long main sequence existence. They shine steadily, dimmer than the Sun but enduring far beyond it. Long after stars like our Sun have faded into white dwarfs, red dwarfs will continue burning quietly. In the distant future, tens or hundreds of billions of years from now, the bright blue stars and yellow suns will have largely disappeared. The galaxy will be populated mostly by red dwarfs and stellar remnants. The night sky, if any observers exist, will look different. The most luminous stars will be gone. Only faint, long-lived dwarfs will remain. Over trillions of years, even red dwarfs will exhaust their hydrogen. Unlike Sun-like stars, they may not swell dramatically into red giants. Instead, they will gradually contract and heat slightly as helium accumulates. Some models suggest they will end as white dwarfs without dramatic nebulae. Their fade will be gentle and extended. The future of stars also depends on galactic evolution. Our Milky Way is on a slow collision course with the Andromeda Galaxy. In about 4 billion years, the two galaxies will begin merging. Over time, their spiral structures will distort and eventually settle into a single elliptical galaxy, sometimes nicknamed Milkomeda. This merger will trigger bursts of star formation as gas clouds compress. For a time, the night sky may blaze with new stellar births, but star formation itself is finite. The raw material for stars, cold hydrogen gas, is gradually consumed or expelled. As galaxies age, star formation rates decline. In the far future, the era of star birth will wane. Fewer new stars will ignite. The galaxy will become a collection of aging remnants and long-lived dwarfs. Astronomers sometimes divide cosmic history into eras. We currently live in the stelliferous era, the age of stars. It began a few 100 million years after the Big Bang and will continue for roughly 100 trillion years. During this time, stars form, shine, and die. After that, the degenerate era begins, dominated by stellar remnants, white dwarfs, neutron stars, and black holes. White dwarfs will cool gradually, radiating away their residual heat. Over quadrillions of years, they will become black dwarfs, cold, dark remnants. Neutron stars may collide or slowly cool. Black holes will remain, accreting matter occasionally, merging and eventually evaporating via Hawking radiation over timescales of 10-100 years or more. The slow dimming sky is not just poetic language, it is a physical forecast. As star formation declines and existing stars fade, the luminous output of galaxies will decrease. The universe will grow darker, not abruptly but steadily. Cosmic expansion adds another layer. Dark energy drives galaxies apart at accelerating rates. In tens of billions of years, distant galaxies will recede beyond our observable horizon. Their light will stretch and fade. Future observers within our merged galaxy may see only local stars, unaware of the broader cosmic web that once filled the sky. Red dwarfs lasting trillions of years offer a counterpoint to this dimming. Around them, planets may orbit stably for vast spans of time. If life arises around such stars, it could persist far longer than life around sun-like stars. The longevity of red dwarfs suggests that the universe's potential for habitable environments extends far into the future. Imagine a civilization orbiting a red dwarf 10 trillion years from now. Their sky would lack the brilliant spiral galaxies visible to us today. They might not detect cosmic expansion easily. The cosmic microwave background would have cooled and stretched beyond detectability. Their universe might appear smaller, quieter, dominated by faint red suns and dark interstellar spaces. Stars burning out is not a single event, but a cascade of endings. Massive stars end quickly and violently. Sun-like stars end gently but decisively. Red dwarfs endure and then fade. Stellar remnants persist as ghostly echoes of former brilliance. Yet even in the dimmest eras, gravity continues shaping structure. Brown dwarfs may collide and ignite briefly. Stellar remnants may interact. Black holes may merge, releasing bursts of gravitational waves. The universe does not freeze instantly. It evolves slowly. There is a strange comfort in the gradual nature of stellar futures. The cosmos does not collapse suddenly into darkness. It transitions across epochs spanning trillions upon trillions of years. The dimming sky unfolds so slowly that any single moment feels stable. Right now, the universe is near its peak of stellar activity. Galaxies glow with billions of suns. Nebulae cradle new stars. Supernovae scatter heavy elements. We inhabit a luminous chapter in cosmic history. Eventually, that chapter will close. The brightest stars will disappear. The average stellar mass will decline. The sky will redden and darken as red dwarfs dominate. And then even they will fade. The future of stars is not tragic. It is cyclical and transformative. Their burning forged the elements of life. Their deaths seeded new generations. Their remnants will shape distant epochs. As you imagine the slow, dimming sky, picture it not as sudden night, but as twilight, stretching across unimaginable time. The universe aging gracefully, its brilliance softening, its light thinning gently. Stars are not eternal, but their lifespans dwarf human scales. The sun will shine for billions more years. Red dwarfs will glow for trillions. The cosmos moves patiently, unconcerned with urgency. In the far future, when most stars have burned out and galaxies drift apart, the memory of luminous skies will exist only in ancient light, still traveling across expanding space. For now, though, the stars shine steadily. Fusion continues in countless cores. Red dwarfs hum quietly. Massive stars blaze briefly. The sky remains bright with points of fire. And in contemplating their future, we glimpse both impermanence and endurance. A universe that slowly dims, yet persists across timescales so vast they soften any immediate fear. The future of stars is a long, quiet unfolding, burning, fading, enduring. A gradual shift from brilliance to hush, a slow, dimming sky stretching across the deep calendar of the cosmos. There is something strangely calming about thinking far enough ahead that all urgency disappears. Not tomorrow, not 1,000 years from now, not even billions, but trillions upon trillions of years into the future, when the stars have dimmed and galaxies have drifted far apart. The end of the universe is not a single prediction, but a set of possibilities, each shaped by the same quiet forces we observe today. Heat death, big rip, big crunch, cosmic fate unknown. To understand how everything might end, we begin with how it is expanding. Since the discovery in the late 1920s that galaxies are receding from one another, we have known that space itself is stretching. Later observations revealed something even more surprising, that expansion is accelerating. Galaxies are not just moving apart. The rate at which they separate is increasing over time. This acceleration is attributed to dark energy, a pervasive component of the cosmos that behaves like a repulsive force woven into space-time itself. The long-term behavior of dark energy determines much of the universe's destiny. If it remains constant, as current observations suggest, the most likely scenario is heat death. Heat death does not mean fire or explosion. It means equilibrium. It means a universe that has exhausted usable energy. Over immense spans of time, stars burn their nuclear fuel and fade into white dwarfs, neutron stars, and black holes. Star formation gradually ceases as gas is consumed or expelled. Galaxies merge and settle into quiet elliptical forms. After roughly 100 trillion years, the stelliferous era, the age of stars, ends. What follows is a long twilight. White dwarfs cool slowly, radiating residual heat into space. Neutron stars gradually lose energy. Black holes persist longest of all, consuming stray matter and occasionally merging with one another. But even black holes are not eternal. Through Hawking radiation, they very slowly evaporate, losing mass over inconceivably long periods. A supermassive black hole may take 10 to 100 years to vanish. As expansion continues, galaxies outside our local group will drift beyond our observable horizon. Their light will stretch and fade until it is no longer detectable. Future observers, if any exist in the distant epochs, may see only the stars within their merged galactic remnant, unaware of the once vast cosmic web. Eventually, after the last stars have faded and black holes have evaporated, the universe approaches maximum entropy. Matter decays. Energy becomes evenly distributed. Temperatures approach absolute zero. No gradients remain to drive processes. No engines burn. No structures evolve. This is heat death, a universe in thermodynamic equilibrium, not destroyed, not shattered, simply quiet, cold, and diffuse. It is not dramatic in the way human endings are dramatic. It is gradual and patient. Over time, so long that language strains to describe it, the cosmos cools into stillness. But heat death assumes dark energy remains constant. If dark energy behaves differently, if its density increases over time, the future changes profoundly. This leads to the second possibility, the Big Rip. In the Big Rip scenario, dark energy grows stronger as the universe expands. The acceleration intensifies. Galaxies recede faster and faster. Eventually, gravitationally bound systems begin to unravel. First, galaxy clusters disperse. Then galaxies themselves are torn apart as space stretches faster than gravity can hold stars in orbit. Later still, planetary systems are disrupted. Planets drift away from their stars. Eventually, the stretching becomes so extreme that even atoms cannot remain intact. The fabric of space-time expands so violently that molecular bonds break, atomic nuclei separate, and fundamental particles are pulled apart. The timeline depends on the strength of dark energy's increase. In some speculative models, the final tearing could occur tens of billions of years from now. In others, far later. As of current measurements, dark energy appears consistent with the cosmological constant, meaning its density does not grow. But uncertainties remain. Observational refinements continue. The Big Rip is dramatic, a crescendo of expansion ending in dissolution. Unlike heat death, which cools gradually, the rip accelerates toward a finite moment when structure itself fails. There is also a third possibility rooted in gravity rather than expansion, the Big Crunch. If dark energy were to weaken or reverse sign, gravity could regain dominance. The expansion of the universe might slow, halt, and eventually reverse. Galaxies would begin moving toward one another. The cosmic scale factor would contract. Temperatures would rise as matter compresses. In this scenario, the universe's expansion is not eternal. Instead, it mirrors the Big Bang in reverse. Over billions of years, galaxies merge in an increasingly crowded cosmos. Background radiation grows hotter. Eventually, the entire universe collapses into a dense, hot state, a potential mirror of its origin. Some cyclic models propose that such a crunch could lead to another Big Bang, initiating a new expansion phase. The cosmos would become oscillatory, expanding and contracting across epochs. However, current observations suggest that expansion is accelerating, making a crunch unlikely under standard dark energy models. Still, the possibility remains in certain theoretical frameworks. If the nature of dark energy changes over time, cosmic contraction could occur far in the future. Heat death, Big Rip, Big Crunch, each depends on how dark energy behaves and how gravity responds. Yet the cosmic fate remains unknown. Modern measurements of cosmic expansion, the cosmic microwave background, and large-scale structure provide strong evidence that the universe is flat and accelerating. These data support the heat death scenario as most probable, but physics evolves. Our understanding of dark energy remains incomplete. We do not yet know whether it is truly constant or dynamic. Beyond these three scenarios, there are more exotic possibilities. Vacuum decay, for example, arises from quantum field theory. If our universe resides in a metastable vacuum state, a lower energy configuration could exist. A quantum fluctuation might trigger a bubble of true vacuum expanding at near light speed, altering physical constants instantly within its domain. Such an event would propagate across space without warning. This remains speculative, but it reflects the depth of uncertainty at fundamental levels. Another concept involves proton decay. Some grand unified theories predict that protons are not absolutely stable. If protons decay over extremely long timescales, perhaps 1034 years or more, ordinary matter would gradually dissolve. Even white dwarfs and neutron stars would disintegrate into radiation and elementary particles. Each possibility stretches beyond ordinary intuition. Human lifespans are measured in decades. Civilizations span centuries. Stellar lifetimes stretch billions of years. Cosmic endings unfold over trillions or beyond. It is worth noticing that none of these scenarios imply abrupt annihilation in our foreseeable future. The universe's end lies so far ahead that it does not press upon present existence. The sun will shine for billions of years. Galaxies will continue forming stars for trillions. The contemplation of cosmic endings can feel sobering, but it also invites perspective. The universe is dynamic, not static. It began in a hot, dense state and has evolved continuously. Its end, whatever form it takes, will be another phase in that unfolding. Heat death is quiet. Big Rip is violent. Big Crunch is cyclical. Cosmic fate unknown. Perhaps the most honest conclusion is humility. We know that expansion accelerates. We know dark energy exists, but its nature remains elusive. Our models extrapolate far beyond current observation. Small deviations in parameters could alter distant futures. As you imagine trillions of years hence, picture the sky slowly thinning, galaxies fading beyond reach, stars burning out one by one, or alternatively, space stretching ever faster until structure dissolves, or gravity gathering everything inward in a final convergence. Each vision belongs to physics, not myth. Each emerges from equations describing spacetime's evolution. Yet each remains provisional, subject to refinement as data improves. The end of the universe is not imminent. It is a horizon beyond imagination. It does not threaten. It invites reflection. The cosmos has endured nearly 14 billion years already. It has transformed from plasma to galaxies to life-bearing worlds. It may continue transforming long after we are gone. Heat death suggests equilibrium. Big Rip suggests tearing. Big Crunch suggests return. The truth may align with one or surprise us entirely. Cosmic fate unknown. And perhaps that uncertainty is fitting. The universe began in mystery. It continues in mystery. Its ending too rests in possibilities rather than certainty. For now, stars shine. Expansion continues. Entropy rises gently. The story of the cosmos unfolds in the present moment, unconcerned with distant finales. And somewhere within that vast unfolding, awareness contemplates endings not with fear, but with quiet wonder at the scale of existence itself. There is a quiet comfort in stepping back far enough that your entire life fits inside a single breath of cosmic time. Not as a dismissal, not as something insignificant in a cruel sense, but as a gentle recalibration. The universe is vast beyond ordinary language. It has existed for nearly 14 billion years. It will likely persist for trillions more. Against that backdrop, our worries, our deadlines, our racing thoughts soften. They do not vanish. They simply shrink into proportion. We are stardust. This is not poetic exaggeration. Every atom heavier than hydrogen and helium inside your body was forged in a star. Carbon formed in stellar cores. Oxygen emerged from fusion reactions deep within massive suns. Iron was created in the final moments of supernova explosions. The calcium in your bones, the nitrogen in your cells, the phosphorus in your DNA, all of it assembled through processes that unfolded long before Earth existed. Stars lived and died so that matter could rearrange into new forms. Their explosions scattered enriched elements into space. Clouds of gas collapsed again under gravity, forming new stars and planetary systems. On at least one small planet orbiting an ordinary star, those elements organized into chemistry, then biology, then awareness. You are not separate from the cosmos. You are one of its configurations. When you look at the night sky, you are seeing the source material of your own body shining at a distance. The atoms in your bloodstream were once inside stellar furnaces. In a very literal sense, the universe has folded inward upon itself and become conscious. Matter that once drifted between stars now contemplates stars. There is something deeply reassuring about that continuity. You are not an intrusion in the universe. You are an expression of it. The universe is vast and patient. Galaxies drift slowly under gravity. Stars burn steadily for billions of years. Red dwarfs will glow for trillions. Black holes evaporate over timescales so immense that even imagination strains to follow. Nothing in the cosmos rushes. Expansion unfolds gradually. Entropy increases gently. Even dramatic events like supernovae are rare in human lifetimes. Compared to this patience, our anxieties are brief flashes. A difficult week, a challenging conversation, a decision that feels overwhelming in the present moment. These experiences are real, and they matter within the scale of a human life. But when placed beside cosmic time, they are momentary ripples. Imagine compressing the entire history of the universe into a single calendar year. The Big Bang occurs at midnight on January 1st. The Milky Way forms in early spring. The sun ignites in September. Dinosaurs appear in late December. Humanity emerges in the final minutes before midnight on December 31st. Recorded history occupies the last few seconds. Your individual life within that scale is less than a blink. And yet, Within that blink, awareness arises, meaning forms, love exists, curiosity burns. The smallness of our duration does not erase significance. Instead, it makes each moment luminous. Cosmic smallness is not about being unimportant. It is about being part of something larger than ego. The universe does not revolve around our concerns, but it also does not oppose them. It simply unfolds. When thoughts race late at night about the future, about uncertainty, about mistakes, it can help to widen perspective. The Milky Way contains hundreds of billions of stars. Beyond it lie hundreds of billions of galaxies. Light from distant quasars began traveling toward us billions of years before Earth formed. The cosmic microwave background still drifts through space, a faint echo of the early universe. Against this backdrop, your existence is improbable and extraordinary, a configuration of atoms able to feel, to reflect, to imagine cosmic history. The comfort of cosmic smallness lies in release. You are not required to carry the weight of the entire world. The universe has existed without you and will continue after you. That is not a threat. It is permission to rest. We often imagine ourselves at the center of our struggles. Our minds circle around personal narratives, but when viewed from a cosmic vantage point, each narrative becomes a brief story within a vast anthology. Think of the Earth itself. A small planet orbiting a medium-sized star on the outskirts of a spiral galaxy. From space, national borders vanish. Personal identities blur. The planet appears as a fragile blue sphere wrapped in thin atmosphere. All human joys and sorrows unfold within that narrow layer, and even Earth is temporary. In 5 billion years, the sun will expand into a red giant. Oceans will evaporate. The surface will change beyond recognition. Yet this does not diminish the present. It heightens it. The universe is vast and patient. It does not hurry. It does not demand. It allows processes to unfold at their own pace. Your heartbeat is part of that unfolding. Your breath is part of that unfolding. Even your worries are part of that unfolding. Brief electrical patterns in a brain composed of star-forged elements. Consider entropy, the arrow of time that carries everything forward. Stars burn fuel, galaxies evolve, black holes evaporate. You too move through time in a steady flow, but within that flow there are pauses, moments of stillness. Right now, perhaps as you listen or read, there is quiet around you, a dim room, a faint hum of distant sound, the knowledge that outside, above, space stretches silently in all directions. We are stardust, yes, but also storytellers. The universe through us reflects upon itself. That reflection need not be anxious. It can be gentle. Against cosmic time, our worries are brief. The project deadline, the unresolved tension, the uncertain path ahead, each will pass. Not because they are trivial, but because everything passes. The galaxies will continue drifting. The stars will continue fusing hydrogen. The cosmic web will stretch across dark expanses. Long after today's concerns dissolve, the universe will remain in motion. There is relief in recognizing that you are not responsible for holding it together. Gravity holds galaxies. Nuclear forces bind atoms. Dark energy drives expansion. The laws of physics hum along without consultation. Your role is smaller and simpler. To experience, to notice, to exist for a short time as conscious matter. Smallness can feel freeing. When you stand at the edge of the ocean and watch waves roll in, you do not attempt to control the tide. You witness it. The cosmos is a deeper ocean still. Perhaps your breath has slowed as you imagine these scales. Perhaps your shoulders have softened. There is no urgency here, no demand for conclusion. The end of the universe will come in some form, heat death or something stranger. But that lies trillions of years ahead. Tonight the stars shine steadily. The earth turns quietly. Your mind, once busy, can begin to rest. You are a temporary pattern in a vast sea of patterns. Not insignificant, just brief. Like a spark in a great fire. Like a wave cresting before dissolving back into the ocean. And there is comfort in that. The universe is vast and patient. It does not rush you. It does not judge you. It simply allows you to be here for a while. We are stardust arranged into awareness. We arose from ancient explosions. We look outward at galaxies. We wonder about beginnings and endings. And then gently, we sleep. Let the scale of it settle in. Billions of years behind you. Trillions ahead. The sky above wide and quiet. Your worries are small in comparison, but so is everyone's. That is not isolation. It is shared humanity beneath shared stars. The cosmos has room for you, room for your thoughts, room for your fleeting existence. And as you drift now toward rest, remember this simple truth. You are part of something immeasurably larger, yet you are not required to carry its weight. The universe will continue expanding while you sleep. The stars will continue burning, and tomorrow, in this small and precious window of time, you will wake again beneath the vast and patient sky.